So the first speaker is Professor Hong Liu from the MIT. He will give the 3 lectures on the emergence of the space and time in holography. Yeah, please welcome him with yeah, please start.
Okay, yeah. Thanks a lot for the invitation. So it's a great pleasure to give the talk at this conference. So I will be talking about some work which we did recently with my student Sam Nuthauser, and which 2 papers appeared last year, and then there's some new papers to appear soon. So here is the rough plan for the for my lectures. So first I will outline the questions we would like to address and the main ideas, the main slogan to address them. And then I will talk about the most important mathematical structures we will use to discuss those questions. So that includes, say, a few words on modular algebras and why we should care about them, and also talk about the structure, say, of a quantum field theory in the larger limit. And then I will talk about, say, how to use, say, the field theory, the boundary theory to understand the emergence of horizon, Kruskal-like times, and associated causal structure, say, in the ADS internal black hole. And then I will talk about the general formulation of duality for general Bach subregion. And so subcase of this general duality is the so-called subregion duality, which has been discussed a lot during the last number of years. And so here we will give a new formulation. Can be said to, we can derive, say, we can formulate the RT surface without building the entanglement entropy. And then finally, I will have some discussions and the future directions. So roughly, the plan is that the first 2 will maybe the lecture 1, depend on my pace. And then the number 3 will be lecture 2, and then 4 and 5 will be lecture 3. Okay. Good. So normally when we just started talking about quantum gravity, say one of the first problems which appears is the problem of time. So in quantum mechanics, the time is absolute, but in gravity, the most of the time is actually meaningless because it can be changed by arbitrary gauge diffeomorphic transformations. Okay, so it's hard to assign an invariant meaning to the time. But in ADS, the situation is better, because in ADS, actually, there's about absolute asymptotic time, because the ADS has asymptotic, has a time like infinity, which because of the gauge transformation, they go to 0 at infinity, so the time at infinity is actually absolute. Of course, this underlies the success of the ADS-CFT correspondence. And this is also a reason, one of the reasons that the quantum gravity in space-times of other asymptotics are much more difficult because they don't have a time like infinity. They don't have this absolute boundary time. But still, even in the context of ADS-CFT, even given this absolute asymptotic time, there's still many puzzles related to the Bach time evolution. Okay, still in the Bach of the space-time, the time still can be changed in the arbitrary way by diffeomorphism transformations. Okay, so how do we understand them? So in some simplest case, say if you have a static geometry, so you have a global, say, time like a Killing vector for your full space-time, and in this case, then the story is very simple. You can just extend this asymptotic time to the interior because essentially there's a preferred time slice for the whole geometry. And but in general time-dependent case, the story is far from clear. Okay. So so a very interesting intermediate case between the static geometry and general time-dependent cases is internal black hole in ADS. Okay, so this is the one of the best known part of the duality of ADS is that the internal black hole in ADS is conjectured to be dual to two copies, say, of the CFT in the thermal field double state. So this ADS internal black hole geometry is interesting. It's because there's a time-like Killing vector outside. So there's an even horizon, and there's this region R and L, which is outside the horizon. And in the region R and L, there is a time-like Killing vector, okay, and there's a boundary. So the boundary time can be easily extended, yeah, because there's to the region R and L. Okay, so this explains, say, our in the sense it's very easy to understand the physics of R and L in the R region and L region using the standard ADS CFT dictionary. Just because the time here is very easy, we can just extend the boundary time to this region. But as we know that the spatial time actually stops at the horizon. Okay, and so it's a natural associated with this. There are many mysteries. Say how do we understand this future and the past region from the boundary? Because the time here is not cannot described easily using the boundary time. Okay, and also in the Bach we can access the future and the past region using the Kruskal-like time. And say if you consider infalling observer roughly follows this Kruskal-like time. And but again, that kind of time is mysterious from the boundary perspective. Okay. And also, how do we understand the horizon and associated causal structure, say from the boundaries perspective? And also, even though in this thermal field double state, the CFTL and the CFTR, they're not interacting with each other. But actually in the Bach, we can actually send observers into the future region and they can interact. Yeah, so the degree of freedom from R and L, they can interact by falling into the black hole and interact in the future region. Okay, so how do we understand this from the boundary perspective? Okay, so all are, say, partly mysteries, say, associated with this internal ADS black hole. And a lot of related puzzle, which has been, say, puzzling people for many years, is to understand the time, say, in the Wheeler-DeWitt patch. So let's imagine we have just global ADS, which is a cylinder, and then you have a time. Okay, you have this absolute boundary time. And so for the global ADS, say, if you are in the empty ADS, then you can extend this boundary time to the interior. And then, yeah, so we understand that very well. But there's a mystery associated with this Wheeler-DeWitt patch. So let's consider just a causal diamond, okay, in the Bach, and they say associated with this Cauchy slice, this dashed line. And so this causal diamond in the Bach is associated with only a single time, okay, naively only associated with a single time in the boundary. But clearly there is a non-trivial evolution in the Bach within this causal diamonds. Okay, so how do we and this time inside the causal diamond certainly is not related to the boundary time, right? Yeah, at least not directly related to the boundary time. So how do we understand this kind of evolution? Okay, from the boundary perspective. And more generally, we would like to understand in holography how the Bach space and time really emerges from the boundary theory. Say more generally consider say a Bach space time, okay, due to some state in the boundary, and some local space time region in it. Okay. So ideally we would like to understand how do we describe such a region in the boundary theory. Okay, just some arbitrary local space time region in the Bach. And then how do we describe the boundary? How do we give boundary description of the internal time inside this region? Okay, so this is example of this, say, Wheeler-DeWitt patch, which I just showed. And also, how can we use the boundary theory to describe the causal structure, say, associated with this region? So for example, this Wheeler-DeWitt patch clearly is associated with this causal structure. There's a night cone, which defines the this diamond. And similarly, in the black hole case, we have this horizon, which determines the causal structure of this space-time. Okay, so these are just special examples for more these more general questions. How do we understand the causal structure associated with the arbitrary space-time region in Arc? Okay. And then how do we give the boundary description, say, of some kind of global time, which actually can take you outside this region? So if you have a space-time region, then there's an internal time inside the region, but you can also because this is part of your only some sub-region, then you should be able to also go outside the region. And so this is related to this Kruskal time for the black hole story. Okay. So I will try to give a framework, try to answer this kind of these questions. Okay. So before doing that, it's important actually to emphasize one point. Is that geometric notions such as local space-time regions, horizons, or time, etc., space or time, they are sharply defined only in the G-Newton goes to zero limit. So here we always take h bar to be 1, okay, and then the gravity, so the classical gravity regime is the G-Newton goes to zero limit. And only in this limit we can talk about those geometric concepts in the mathematically precise and sharp way. Okay. So at finite G-Newton, so if you had finite G-Newton, then quantum space-time fluctuations will make such kind of geometric concept fast. Okay, so we expect the space-time will fluctuate. Then it's hard to talk about the specific region. It's hard to talk about horizons, etc. So right now, we don't yet have a proper language to describe, say, quantum gravity in this kind of regime. Okay, so the gravity we can sharply talk about this all in the perturbatively G-Newton goes to zero limit. So also I should mention that by G-Newton goes to zero limit, I don't mean that strictly the G-Newton is equal to 0. It just means the perturbative expansion in small G-Newton to any finite order. Yeah, as we normally do in semi-classical expansion.
So I have a question in here. So
okay,
so correction is 1/n, or it's non-perturbed, like some exponential separation. When you say geometric concept is fuzzy, it's like the.
Sorry, say it again.
Here the geometric concept. You said geometric concept is fuzzy, and does it mean that this is a 1/n effect, or it's exponentially suppressed some non-perturbative effect?
Here by G-Newton goes to zero limit, that just means perturbative expansion in G-Newton. And at this finite n, that just means the exact finite n. Yeah, not doing any approximation.
Okay.
Yeah.
Thank you.
So this means that the questions of emergence of space and time can only be formulated sharply in the G-Newton goes to zero limit. Okay, so that's the playground we are going to which we are going to work with. And so this translates into the boundary theory from this standard relation. So G-Newton is inversely proportional to n, and it's a number of degrees freedom for the boundary theory. And this translates into the n equal to infinity limit, say in the boundary theory. So here we are not talking about any specific example, but you should always keep some examples in mind. For example, n equal to possible Yang-Mills theory with SU engaged group, or some kind of 2D CFT in the large central charge limit. Okay. And so in order to understand this kind of emergence of space-time, say in this kind of Nigerian limit. And so important step is actually pinpoint, okay, the precise mathematical structure, so that it is responsible for this emergence of various geometric notions. So here we know that somehow when you go to G Newton goes to zero limits, and then this kind of geometric concept becomes sharp. Okay, so that means that from the boundary theory point of view, when you go to Nigerian limit, something geometric must happen. Okay, so that this kind of geometric concept somehow emerges when you take n go to infinity limit. Okay, if you have an exact finite n, you will not be able to talk about those concepts in a sharp way. Okay, and again, by saying n go to infinity limit, I mean you can walk perturbatively in 1 over n expansion to any finite order. Okay, just perturbatively to any finite order. Here, yeah, that's what I mean. Say n go to infinity limit. So the things which I will play a very important role in my discussion for this emergence of the space-time, box space-time from the boundary perspective, is to show that there's a ubiquitous, say, emergence of type 3-1 Modular algebra, Modular sub-algebras in the boundary theory in this n go to infinity limit. Okay, so this is something only appears, okay, in the n go to infinity limit.
Can I ask the same question in here? So in the shifting, if you consider large n limit, and then if you can study the like a 1 over n correction, just one next level, and like a maybe second order, then in that order, can we see the sharp horizon, or it's not possible to see the sharp horizon in the 1 over n correction?
Right, it's always the horizon is always sharp. It's because of just by definition of the perturbative expansion, because the zeroth order is always much larger than the you always expand. You can see indirectly. Say effect due to say some kind of quantum correction to the horizon when you do 1 over n expansion to finite order. But the horizon itself, it's always expanded around say n equal to infinity just by definition, and so you can pinpoint a precise horizon structure. Yeah.
Okay, thank you.
Yeah. So for example, just in the gravity aside, say when you do G Newton expansion, and G Newton expansion is around some geometry, and so perturbation theory is always around that geometry. That geometry is the background. It's the sharp background you define your G Newton expansion. Yeah.
Hi, I think that in the gravity theory of conformal fields side, we have some unbounded operators. But for this kind of unbounded operator, we should also speculate some emergence layer. I say we should still expect the emergence space-time layer. So, but we know that the Holographic algebra is only for the bounded operator. So could I say that the emergence space-time may not be relevant to the Holographic algebra?
Yeah. So I think so this is a very so from my perspective, I think whether it's bounded or unbounded is not important. So for unbounded operator, you can find some way to make it into a bounded operator. Say and so I believe this is a technical question. It's not a conceptual question. Is that you can it's enough just to work with the bounded operators.
Okay, thank you.
Yeah. So in my discussion, I assume this distinction is not so important. Yeah.
Okay.
Yeah. So I will not be very precise about how to say or in what way to turn an unbounded operator into a bounded operator, etc. Yeah.
Because I remember that your paper mentioned that your algebra is type 1 volume and you also boundedness. I remember you write so.
Sorry, say it again.
I remember that your paper make sure that the operator is bounded.
Yeah. So in order to talk about the Modular algebras, indeed, they only apply to bounded operators.
Yeah.
And yeah, but of course, normally when we work with quantum mechanics, when we work with X and P, etc., they are all unbounded. And but there's a way to make, say, X and P. You can differentiate them to look at this wild algebra, etc. Yeah, so I believe this thing you can always make just for the important physical questions, and it's enough just to look at the bounded operator algebra. Yeah.
Simple question. So for finite the G, then the definition of the horizon is not well defined for finite gravitational constant.
Yeah, indeed. So the answer to this question is not known. Because right now we don't really have a language. We don't even have a language to talk about this question. Say at finite G Newton, exactly finite G Newton, how do we even define a horizon? We don't really have such a language yet.
Okay, thank you.
Yeah, so that means that at finite n, we cannot really, we don't really have a language to talk about, say, the Bach geometry. So we have to work with angle to infinity limit. Okay, good. So here is the slogan I want to convey, is that the Bach spacetime is actually can be considered as a geometrization, say, of this emergent boundary time type 3-1 algebras. So more explicitly, so I will argue there is a one-to-one correspondence with emergent this type 3-1 Modular algebras, a sub-algebra in the boundary theory with Bach space-time region. Okay, so when I say Bach space-time region, I will always refer to, say, causally complete Bach space-time region. It's always some kind of yeah, you always causally complete it. Okay. And so even more explicitly, so I will argue that the for emergent type 3-1 Modular algebra, there's a Bach operator algebra. It can be identified with some Bach operator algebra in some space-time region. So that's how we associate, say, a space-time region with such a Modular algebra. Okay, and in particular, the properties of this emergent type 3-1 sub-algebras can be used to derive, say, geometric notions, say, such as horizon, different times, causal structures in the Bach, etc. And yeah, so more generally, this can be considered as a duality for the general Bach space-time regions. Okay. And so this generalized the standard sub-region and sub-region duality. Yeah. Okay, any questions? Okay, good. So now let me talk a little bit about why we actually care about the Modular algebras. Okay. So first, let's just consider, say, suppose we are interested. Yeah, let's just consider a simple question. Suppose we are interested in entanglement, say, bipartite entanglement of a quantum system. So the standard story is, say, let's divide this quantum system into two parts, subsystem 1, subsystem 2, and we assume that the Hilbert space can be factorized into those for the subsystem 1, subsystem 2, so H1, H2, and then for any states of your theory, you can say, for example, you can trace out all the degrees freedom. Say in subsystem 2, you get this reduced density matrix, say for subsystem 1. And this reduced density matrix contains, say, essentially contains all the quantum information about the entanglement, say, between 1 and 2. And for example, yeah, so one observable we often consider, say, is the entanglement entropy, which you just take the Modular entropy for this rho 1. Okay, so this is the standard story, and so if you know rho 1, you can essentially compute anything you want. Yeah, any observables you want to to probe the quantum information of the system. Yeah, the entanglement correlation between 1 and 2. But in the special case, then there's actually additional structure. Okay, so it's in the special case when both row 1 and row 2. You can also do row 2, which you trace out. You take the psi, you trace out the subsystem 1. So in the special case, when both row 1 and row 2 are full rank, okay, means they actually they can be invertible. So this corresponding to a highly entangled case. Because if we say if they are not entangled, then row 1 will be just a pure state. Okay, and the pure state certainly is not a full rank, not be inverted. Okay. And so when row 1 and row 2 are full rank, then you can now construct the new operator. So normally called the modular operator this way. So delta is equal to row 2 times row 1 inverse. Okay, and you can also, and the delta is inversible, can be inverted. Okay, because both row 1 and row 2 are inverted. And this modular operator have the simple property is that if you act on the, say, if you exponentiate it, say with imaginary exponent, and then act on the operators, say for subsystem 1. So this BH1 denotes the operator, say the operator algebra, say of the system 1, and then you take the operating system 1 still to system 1. Okay, and you take operating system 2 still in system 2. So this is very tricky, trivial to see in this case, because delta is just row 2, row 1 inverse. And when you act with operator in system 1 and row 2 just commute, okay, and then of course this just remains in H1, similarly for H2. Okay. So and this kind of unitary evolution is called modular flow. Okay. So existence of modular flow can also be considered as an indication that the two subsystems are highly entangled. So this is the standard story normally we talk about for quantum mechanical systems. But now let's talk about entanglement in the quantum field theory. So in the quantum field theory, let's imagine, say, let's consider entanglement between half spaces in the quantum field theory in the vacuum. Okay, so let's, for example, let's just consider 1 plus 1 dimensional field theory. This is the space. And now imagine you just separate the space into two half space, the left and the right. Okay. And oh, for some reason my this dot, sorry, this dot should be here. Okay. For some reason this dot shifted. Yeah. So this dot should be here. It separated the left and the right region. Okay. And so the standard approach. So now let's try to suppose we are interested in the entanglement between the left and the right region. Okay, and so there's a standard approach to such kind of calculation. Is that if you look at the causal completion of the L and the right, and essentially you just get the Rindler region associated with right and the Rindler region associated with left, and then of course there's also future and the past, the light quantum region, etc. So the standard approach to calculate the entanglement, say between L and the right, is that you calculate the entropy in the regularized Rindler series. Okay, so essentially you look at how these two Rindler series are entangled with each other. Okay, and so the way there are many ways to regularize these two series, and so for example, one way is to put the series on the lattice. Okay, you put the series on the lattice, introduce a short distance cutoff. And now and then you can just use the standard trick, which I described in the previous slides, and to calculate the entropy. But the thing is that when you take the continuum limit, okay, the standard story is that you find the entropy become divergent. Okay? So as the regulator is removed. So if you take this short distance cutoff, the lattice spacing go to 0, and then you find that the entropy actually is divergent. So this is usually blamed on the UV behavior of a QFT, say because QFT, have lots of UV degrees freedom, and that's why the entropy is divergent. So this statement is not wrong, but but does not capture the essence of the issue. Okay. Oh, and now this thought is in the right place. Okay. And this statement is say you blaming this on the UV behavior of QFT is not the wrong statement, but does not start to capture the essence of the problem. And it's more like you say the cancer can make a person die, but of course a person can die in many different ways and not just due to cancer. Okay. So there's a deeper and more fundamental reason for understanding this divergence. So let me just expand this a little bit. So let's first consider the discrete theory, discretized theory. And this story to calculate the entropy in this discretized theory is the standard as just as described earlier. The local Hilbert space factorized for the left region and the right region. So you can factorize your Hilbert space, and then you can calculate the reduced density matrix in the vacuum states. And then you can just calculate the entanglement entropy, which is finite. Okay. So here you can, and then you find the modular flow exists, and the modular operator is factorizable between the left and the right. But now, as I mentioned, if you take the lattice spacing go to 0, then you find the entanglement entropy go to infinity. But if you dig a little bit deeper, and you find that this going to infinity is actually due to some actually rather subtle reasons. Okay. So first, you find actually one reason this you find a reason that this entanglement entropy is no longer well defined. It's actually that when you take the continuum limit, the Hilbert space becomes not factorizable. When you take the continuum limit, it's not possible to factorize your full Hilbert space into a Hilbert space associated with the right and the Hilbert space associated with the left. So this structure no longer exists. So the reason is that in the discrete theory, the states which have this kind of factorized structure, their energy all go to infinity when you take the continuum limit. Okay, and when you take continuum, and then they just drop out of your Hilbert space, and those finite energy states they cannot be factorized. Okay. And because of this lack of factorization, actually the reduced density matrix just does not exist, and so that's why it's related to why the entanglement entropy actually are going to infinite. Okay, it's not fundamentally not defined. So it's not just due to say some bad UV behavior. Okay, it's just fundamentally not defined. But the interesting thing is that in the continuum minimum, actually modular flows exist, and but it's no longer factorizable. Okay, you can no longer write it. Yeah, because here the reduced density matrix no longer exists. You certainly cannot factorize. Okay, but modular flow exists.
I have a question.
Yeah.
But here, for example, you can consider also gauge theory like a Super-Yang-Mills type or any gauge theory. That gauge theory, even in the lattice, can we have some local Hilbert space, like a factorizable Hilbert space?
Right. Yeah. Good. That's a good question. Yeah. So in the gauge theory case, indeed, the story is more subtle. Mm-hmm. So here I'm just using the illustration, even just in the simplest scalar theory, which that kind of subtlety don't arise. That subtlety do not arise. Yeah, just in the gauge theory case, you can still treat it using this discrete story, even though using slightly more fancy techniques. But the fundamentals it's not fundamentally different from the scalar case, which I'm going to mention in a couple of in a couple of minutes. Yeah, just immediately now. Yeah.
Okay, thank you.
Okay. So seemingly, there's also a lot of fundamental difference between the discrete and the continuum limits, which seemingly not related to those features, is that in the discrete case, there's no sharp light cone. Okay, but when you have such a quantum mechanical system, and when you evolve time a little bit, okay, just when you, no matter how small, how little time you evolve, your information can always leak out of the diode cone to infinite distance away. There's always small exponential tail can leak to very large distances. Okay, so in the discrete case, there's no sharp light cone. But of course, we know that in the continuum case, there's sharp light cone, and there's a strict causality, so the commutator becomes zero outside the horizon, outside the light cone. Okay, but in the discrete case, and the commutator is level zero. Okay, and the commutator is level zero whenever you evolve time a little bit. And all these features, okay, all these features, including absence of sharp light cone or existence of sharp light cone, they all can be related to one fundamental fact, is that the operator algebras in the right region actually have different algebraic structure between the discrete and the continuum case. Okay, so in the discrete case, you have actually a type 1 modular algebra, and in the continuum case, you have type 3 modular algebra. Can I ask you a question? Yeah, good. Yeah, let me just make one comment first. Okay. So if you look at the lattice gauge theory, so the lattice gauge theory is more subtle. Naively, you don't have this factorized Hilbert space, but still you can address it using this framework of the type 1 modular algebra. And so fundamentally, it's still even though it's a little bit more complicated, but fundamentally it's very similar. Still treated using type 1, but for the continuum case, there's a fundamental differences. Okay. Yes. What is the typical example of this left-right splitting, which exists for lattice but not in continuum? Sorry, say it again. I didn't hear the question very clearly. Yeah. Mm-hmm. What is the example of this left-right splitting, which exists in discrete but not in continuum? Oh, right. Yeah. So if you have a lattice, say if you have a lattice structure, then because for each point you have a Hilbert space associated with this lattice, and then certainly you can see that the Hilbert space are factorized. Yes, that's clear. Why it goes away when it goes to continuum? Yeah, and another key thing is that if you look at those states which are factorized between right and left, and in the continuum limit, they all have infinite energy. And so those states, they just drop out from the continuum limit. For example, the left moving and the right moving notion is also destroyed in. No, the left moving and the right moving notion is not destroyed. It's just the Hilbert space no longer factorized. I see. Does you certainly can have left moving modes and the right moving modes. Yeah. Does it mean that there is just, it can be cured apart from some anomaly, or it cannot be cured? No. Let me just be a little bit more explicit. So in the factorized theory, so you can consider, say, the right theory and the left theory. Say you can consider the ground state here. Say the 0 right and the 0 left. Okay. And in the discretized theory, the 0 left tensor 0 right is a state of the full system. Okay. But now when you take the continuum limits, then you find such a factorized state, they have infinite energy. So this 0 left, the 0 time, the tensor 0 right, this state have infinite energy, then they just drop out of your Hilbert space. So those states which they survive, they cannot be factorized. There's no factorized structure anymore. Yeah. So let's go and we will see more. Okay.
Hi, yeah, I have one question. When you say that when you define the modular flows, I think you need the modular Hamiltonian. But if you take the continuum limit and you want to say that the Hilbert space is not factorizable, then how do you define the modular Hamiltonian? Right.
Yeah. So this is guaranteed by this so-called the Tomita-Takasaki theory. which guarantee you the existence of the modular flow, which independent. Yeah. So the point is that the modular flow and the modular Hamiltonian is a much more general concept than the factorization of the Hilbert space and the reduced density matrix.
So could I say that this modular flow in the Maison's theorem does not need a modular Hamiltonian defined by a partial trace operation?
Yeah, that's right. That's right. Yeah, you don't
Okay.
need it. Yeah.
Okay, so that is
Yeah,
different from discrete case.
That's right. Yeah. It's a much more general definition, which you don't need to use this kind of partial trace. Yeah.
Okay, I understand. So in some sense, you just extend the definition of the modular flows.
That's right. That's right. Yeah.
Okay, thank you.
Good. So this example just illustrates that this operator algebra perspective can give you much sharper or general ways to think about many, say, seemingly not connected facts. Okay, and if you just say look at the ground state, if you just take the continuum limit, you just find that entropy is divergent. Okay, but this algebraic way tells you what is the fundamental reason for that. And so this is the reason. Yeah. Then you ask, then why normally we don't talk about this operator algebraic approach, say when we talk about the quantum mechanical system. Okay. And the reason we normally we don't talk about this operator algebra approach is because there was a very powerful theorem called the Stone-Monument Euclid's theorem. It said the algebra of observables of a quantum system with a finite number of degree freedoms has a unique irreducible Hilbert space representation, say up to unitary transformations. Okay. So this theorem essentially tells you if you only have a finite number of degree freedom, say if you have finite number of harmonic oscillators, etc. Okay. And then whatever the algebras of your quantum systems, they can all be uniquely associated with some kind of Hilbert space. Okay, just you can just imagine such kind of algebra is associated with some kind of Hilbert space. And if you identify that Hilbert space, and then you identify the algebra. Okay, so this is exactly what we do in this case. Okay, so in the discrete case, in the operator algebra, say for the right region and for the left region, I don't need to talk about them. I can just talk about the right Hilbert space, and that uniquely determines my operator algebra for the right region. Okay, and so when you have a finite number of degrees freedom, and then you just don't need to talk about the operator algebra. You can just talk about using the Hilbert language, Hilbert space language, which is much easier, which is normally what we do. And so that's what we normally do. But this is not true for systems with infinite number of degrees freedom. Okay, for QFT or statistical systems in the thermodynamic limits. Okay, if you look at QFT or statistical limit in the thermodynamic limit, and then this breaks down. Okay, and then your operator algebra actually can have infinite number of representations. Okay, you can no longer find a unique Hilbert space to associate with that operator algebra. So in such a case, then the operator algebra itself actually plays a much more fundamental role than the Hilbert space, because Hilbert space just provides a representation for the algebra. Okay, and the different Hilbert space just provide a different representation for the algebra, and the algebra can have many infinite number of representations. Okay, and so in such a case, the operator algebra actually provides an intrinsic description of the system, and with information not available from descriptions, say in terms of some specific state. So the reason, a lot of the reason we normally don't talk about operator algebra in quantum field theory is that normally, say for particle physics applications or for certain applications, we're interested in the behavior of the QFT in the ground state or in some specific states. Okay, so if you talk about the QFT in some specific states, and then you miss some kind of global information which is encoded in the operator algebra. but those kind of information become very powerful. Say if you want to understand, say some global structure of your quantum field theory, say quantum information of your quantum field theory, etc. And so that's why actually operator algebra approach provides a conceptually superior, even though it's much more mathematical way to think about, say, quantum field theory or statistical systems. Okay, and they provide real powerful perspectives and techniques. So let me just say a few words about the Modular algebras. And so Modular algebras, they say just operate the algebra in the quantum system, but we define it to be closed. Yeah, say it's closed under the product, etc. But it's also closed under the so-called the weak limit. So let me explain a little bit what this weak limit means. So suppose you consider algebra A, this script A, and then you consider some elements, say some sequence of operators in this algebra A. And we say that this sequence converges to some operator in the weak way, okay, weak limit. So if the convergence is satisfied for any matrix elements, okay, so psi and psi, chi are say arbitrary states of your system. So if this convergence is true, say within any matrix element, and we say that the AN converges into A, okay, as a weak limit. Okay. And saying that this operator algebra is closed on the weak limit means that it's supposed that this you have the sequence in A which converges into A, and then this A should also be, this small a should also be in your algebra. Okay, so this is closed. So it turns out that this actually definition actually give you a very rich structure, which I will not have time to talk about. And the one very important thing is so-called the Modular double commutant theorem. It said if you take the double commutant of your algebra A is equal to A itself. Okay, and so this A prime denotes the double commutant of A, just the collection of operators that commute with A. And the double commutant, you just look at the connection of operators commutes with those commute with A. Okay, and yeah, so this so this is a powerful theorem which is very useful in thinking about Modular algebras. And then Modular algebra also has been classified, so really taught in force mathematics, and based on properties of projection operators in the algebra into type 1, type 2, and type 3. And within type 1, type 2, and type 3, they can be also further classified, etc. So we are not going into details into the classification. Let me just quickly mention, say the type 1 algebra is the algebra, for type 1 algebra, you can always find some Hilbert space. And then this algebra will be just algebra of bounded operator in that Hilbert space. Okay. Yeah, so this is the standard finite degree freedom story. Okay, and so operator algebras in any system with a finite number degree freedom is type 1. And yeah, so that's why this type 1 story is very simple. We normally don't even need to think about this algebra. We can just think about the Hilbert space. But for relativistic QFTs, then you can show that for any local region, and the local operator algebra in that region can be associated with type 3-1 Modular algebra. So in the sense that type 3-1 Modular algebra is actually it's a very general feature of relativistic quantum field theory. So I will not talk about the details of how you define this type 3-1 Modular algebra, and you can just think about this feature I listed earlier here to be as say you can think, obtain some intuitive feelings about type 3-1 algebras just from those features. Yeah, because technical definition is a little bit complicated. Okay, good. And then the entanglement for any local region in the quantum field theory then can be understood in terms of modular flows and be associated with such algebraic structure. And so modular flows provide a more general and powerful framework to think about entanglements, and then say reduced density operator, etc., which is an intrinsic type 1 language. So any questions regarding this part?
Well, can I ask you a question?
Yeah.
So is the non-factorizability well applies for a single harmonic oscillator case as well? So
No,
my question is, for example, single harmonic oscillator has a infinite many excitations, right?
No, a single harmonic oscillator just means a single harmonic oscillator is a single degree freedom.
Mm.
Yeah, here by number of degrees freedom, I don't mean the finite dimensional Hilbert space. I mean finite number of x and p's.
Oh, I see. Okay, thank you.
Yeah. So that includes say finite number of harmonic oscillators, and also applies to say finite number of spin systems, etc. Yeah, including both finite dimensional Hilbert space, but also including some of the infinite dimensional Hilbert space case. Yeah.
Hello. Do you mean that the bosonic harmonizer is algebra is type 1?
Yeah. It's type 1. Yeah.
Okay. If we introduce the momentum and the position operator and consider commutation, then we find that the commutation really gives you some minus IH plus something. But we know that if we do the trace operation on the left-hand side and right-hand side, it will give us inconsistent. So this means that the trace operation does not satisfy the cyclical property. So in some sense, we should not expect so in the type 1 algebra. So in some sense, I expect that this algebra should be type 3 because it does not have the trace operation.
No. No, that's not correct. So the type 1 separates into two types. It's type 1n, so n is an integer, and then that's type 1 infinity. So indeed in the type 1n, the trace is defined for any operator in that in your theory. Yeah, it's essentially type 1n is finite dimensional Hilbert space. And when you have type 1 infinity, then you can have infinite number. You can have infinite dimensional Hilbert space, like in the harmonic oscillator. So we know that when you have a harmonic oscillator, the trace is not defined for all operators. It's only defined for a subclass of operators. That's fine. The trace is the trace can be defined, but just for some operators, the trace is infinite. It's not. Yeah.
Okay, so in some way, I said that you just want that some operator in the bosonic harmonic oscillator is a type 1 bonding algebra.
No, it's not. You just say it's a type 1 algebra. Just type 1 algebra allow type 1 infinity algebra allow to have operator without trace. Okay, you can have some operators say in the type 1 algebra without trace. Yeah. The trace is infinite. Yeah.
Okay.
Yeah.
So in the chat, there is a question.
Okay.
One of participants asked a question about the type 2.
Yeah.
What is the type 2? So
yeah, so type 2 you can define using infinite number of say spin half systems, tensor product in a way, and you take the limit in a certain way. So in the type 2 you can define, again, type 2 separate into different cases. You can have type 2 infinity and then type 2 1. And so for the type 2 1 you can have a trace. And for type infinity, you can have a trace, but again, some operators don't have a trace. Yeah, the trace can be infinity for some operators. Yeah.
Hong, I have one question.
Yeah.
So suppose the field theory is free, no interaction exists.
Yeah.
Then all the I guess harmonic oscillator of that free field is supposed to be don't talk to each other. And then do you think this free field theory still have the same problem of the fuzziness?
Yeah. So even for free quantum field theory, say if you have a free scalar field theory, and if you look at the local operator algebra, it's always type 3 1. Yeah, but if you discretize it and then become type 1.
So this has nothing to do with the interaction.
Yeah, have nothing to do with interaction. Yeah.
All right.
Sorry, could you let me ask one more question? So do you want to say that if you can find some operator with a trace operation, then you can say this algebra is type 1?
Sorry, say it again.
So if you can find the some operator to define the trace operation, then you can say this algebra is type 1.
You know, no, in type 2, you can also find the trace. So there's a more subtle definition between them. Yeah, in type 2, you can also find a trace.
Maybe specifically, let's say if you can, but we just need to consider some operator. Then it's okay to say whether it's a type 1 or type 2.
Yeah. If you have a trace, it's either type 1 or type 2. Yeah.
Okay, thank you.
Well, can I ask you one more question?
Yeah.
Well, I got confused when we consider in the momentum space. We got, for example, in case of free field theory, you can diagonalize in the momentum space, and then entanglement entropy in momentum space is just 0 since it seems to be factorizable. But does it mean the algebra, fundamental algebra is different, or it doesn't depend on whether you work in position or momentum space?
Yeah, so yeah, certainly it's different. Certainly different. So here I emphasize is that any local region. So the momentum operator by definition, if you go to momentum space, that kind of operator is non-local from a space-time point of view.
Oh, I see. Thank you so much.
Good. So yeah. So my next topic say but I see it's already close to 1 hour. Yeah, we started maybe a few minutes late because the so maybe let me say a few minutes and I can break. So I emphasized earlier that in order to understand the emergence, say, of those geometric concepts, it's important that we understand the structure in the large N limit, okay, to see what are the new emergent structure in the large N limit. There must be something new, new emergent in large N limit so that we can understand those geometric concepts. And so again, here, let's consider just as a per topic example, the input for super Yang-Mills series with gauge group SUN. Okay. So when you take this n, the rank n go to infinity, so the many states and operators actually don't have a well-defined large N limit. Okay. So when they don't have a well-defined large N limit, and then they essentially drop out. Okay, so those states and operators which don't have a large N limit, they just drop out from your large N limit. Okay, so when we consider the series at infinite n, and that series just don't contain those operators and states. Okay, so this is similar to when we take the continuum limits in the, say, in quantum field theory. We say when you take a continuum limit, many states in the discrete series actually they have infinite energy, so they don't actually have a well-defined limit. So they just drop out from the spectrum, say, of your continuum quantum field theory. So that's how the continuum quantum field theory become non-factorizable. So similarly, something important happens in the large N limits, because many states and operators they don't have a large N limit. And so that means that the structure of the Hilbert space, okay, and operator algebras can undergo dramatic changes in the large N limit. And so I will claim it's this kind of dramatic changes which is responsible for the emergence of those geometric concepts. Okay. So now let me just define what we mean by the operator has a sensible large N limit. So we say an operator has a sensible large N limit if its vacuum correlation functions has a well-defined angle to infinity limit. Okay. So of course, from our, for example, just using this angle to Yang-Mills series as example, so this just immediately takes us to the finite product of single trace operators, because the familiar scaling properties of correlation function of the single trace operators, and then then that just lead to that. And also here, just emphasize the single trace operators are due to the fundamental field on the gravity side. Okay, so this play a very important role because they have to survive. Because on the gravity side, we do have fields on the gravity side, and so it's those single trace operator which survive. And then so those single trace operators, they don't form an algebra at finite n, but they actually form an algebra in the large n limit. Okay, so we will often call this a single trace operator algebra. So yeah, just they form algebra on the product, say ordinary product. So a key feature in this large n limit, okay, which play a very important role in my discussion later, is that the single trace operator at different times are actually independent. Okay, so let me explain what this means. Okay, let's just consider, for example, in the for Sobe-Amel series, let's just consider this simple example, just trace f squared. Okay, so this is the example we're familiar with. So now let's consider at finite n, we can let's just forget about we'll suppress the spatial dependence, which is not important. So suppose the series at finite n, then this is just ordinary quantum field theory. So we can write the operator at time t, say in terms of standard evolution, Heisenberg evolution, and then you can express it in terms of the operator at t equal to 0. Okay, you can just solve the Heisenberg equation. Say if we are powerful to solve the Heisenberg equation, and then we can express the Vt in terms of operator at t equal to 0. So that just tells you that the operator at any finite time are not independent from the operator algebra at the t equal to 0. So algebra at t equal to 0 is enough to determine your operator at any time. Okay, so this is for the standard quantum field theory, finite n. But in the large n limits, something interesting happened. That Vt is still well defined using the way I'm defining the operator earlier, because the correlation function of Vt is well defined in the vacuum, because this is just single trace operators on finite time, and they obey the standard factorization properties of large n limit, etc. Okay, so this Vt can be defined through limit of its correlation functions. Okay. So Vt is well defined, but now the right-hand side are no longer well defined. Okay, so the Vt can be defined, but this definition of Vt no longer exists in the infinite n limit, because neither of those quantities actually inside this box actually have an infinite n limit. So the first expression does not have an infinite limit, is because the h is equal to because the Hamiltonian have the structure which is n times the trace. Okay, because of this explicit dependence on n, this evolution just no longer well defined in the large n limit. Okay, can no longer make sense of this operator. And similarly, if you look at the sets of O, yeah, it's just closely related to that. This is no longer well defined in the large n limit. Is that the sets of O appears on the right-hand side of the equation. This OI will appear at t equal to 0. They contains not just single trace operators. They also contain complicated operators that do not survive in the large n limit. So that means that this expression itself does not have a sensible limit in the large n limit. So now we have a situation that Vt is defined in large n limits, but its definition, its standard definition is not well defined in large n limits. Okay. So that means a single so this means that single trace operator Vt cannot express in terms of the single trace operator t equal to 0 in the large n limit, because in large n limit only single trace operator survives. Okay. So different from the finite n, different from the standard quantum field theory, the single trace operator at Vt are not cannot be expressed in terms of the algebra operators at t equal to 0. Okay, so this is a simple but a very fundamental fact which I use over and over later. Yeah. So emphasize that where simple looking, so this VT, so trace F squared T is a simple looking operator. But in terms of this OI, I mentioned that this OI actually can contain very complicated operators. So this VT is actually extremely complicated operator defined by large N. Okay, and so but such an operator actually survives in the large N limits. Okay, through the definition of the correlation functions. Okay, through the definition of correlation functions. Okay, good. So I think I'm reaching the 1 hour time. So should I stop here and continue later?
Yes, we can continue in the next session, but maybe we can take a more question. Is it okay?
Oh, right. Okay. Yeah. Let me just finish one more slide. Yeah, here.
Okay. Yeah, sure.
Not related. Yeah. So this means, so let's consider causal diamond. So if you consider standard quantum field theory, or the n-equal super Yang-Mills theory at the finite SUN, so the algebra associated with this Cauchy slice, say I call A1, and algebra associated with this Cauchy slice, they're equivalent. It's because every operator on this slice can be expressed in terms of the operators on A1 through the Heisenberg equation. Okay, but due to the reason I said earlier, for algebra of single trace operators, A1 and A2, they're just independent of each other. Okay, they have not, the A2 cannot be expressed in terms of A1. Okay, and so they're independent algebras. Yeah. So let me stop here. Do you have other questions?
Thank you very much for the clear and great lectures. Please ask any question.
Yeah, I have a question. So what is the qualification of these so-called basis operators, OI? If you don't define it, then probably it can cause some misunderstanding.
Sorry, which operator? I don't
OI.
define it.
OI.
Hmm? Oh, OI. Oh, yeah, OI, just in principle, to solve OI, you have to, we don't know how to work out OI explicitly. We just know in principle how you can in principle work out OI. Say if you are able to solve the Heisenberg equation exactly, and then you yeah, for example, in the case of harmonic oscillator, we can solve any operator, say at any time in terms of operators at t equal to 0 by solving the Heisenberg equation. So here in principle you can do it, but in practice, of course, we don't know how to do it.
No, what I mean is that maybe somebody wanted to say that for some specific time t, and maybe OI can be just just the VT itself. And what do you want to say about it?
So you mean for
so
the free?
why VT cannot be, for example, why VT cannot be one of the OI?
Oh, yeah, OI can include V. OI can include V, but OI also include many other things. OI can include the V itself. So this is a superposition, in principle, superposition of all operators at t equal to 0.
So then isn't it true that just for some t, VT can be expressed as just one operator? So, but you don't want to say that what you want to say seems to be that as time goes on, this time evolution operator cannot be expressed as a finite sum of the basis OI. Maybe I misunderstand.
Yeah, I'm just saying that the VT cannot be expressed in terms of the single trace operator alone.
Yeah, right. So, but the VT itself can be a single trace operator, no?
Yeah, but VT is actually very complex. Even though we call VT a single trace operator, but VT is actually in essence a very complicated operator. That's what I've emphasized here. So if you write, say if you introduce a basis of operator at t equal to 0, and VT will be in general will be some very complicated operator in your some standard basis.
I see. So single trace operator is one condition.
Yeah. Yeah, just single trace operator at finite t can be very, very complicated in principle because of this kind of evolution. Yeah, so so that's why this is often very confusing, because when we look at the VT, we say, oh, this is a very simple operator. But in essence, this is a very complicated operator.
Okay, thank you.
Yeah, so this is also what people, there's one terminology people sometimes use. When you view the VT as operator at t equal to 0, and people call this precursor operator, which are often very complicated, etc. Yeah, even though it looks very simple. Yeah.
Well, can I ask a question?
Yeah.
Okay, so I think you said that for sensible large n limit, we need a finite product of single trace operator. What about the multi-trace operators?
Yeah, multiple trace operator automatically included because we just have because we can have a product. Yeah, because this is algebra.
Oh.
So the multiple trace operator are generated by product of single trace operators.
Right. I see. Okay, good. Thanks.
I have some question about simple question about the type of Von-Neumann algebras.
Okay.
So in the usual quantum mechanics, that can be represented as a matrix algebra. Then it with a finite matrix, then it would be type 1 to the n.
Yeah, type 1n. Yeah.
And my question is, in the some usual position space or momentum space, is it the type 1 to the infinite or on type 2 or 3 or?
You say in momentum space?
Yes, the usual thing that we do in quantum mechanics.
Yeah.
So,
you're talking about harmonic oscillator?
Not the harmonic oscillator, but some wave functions or. That cannot be represented as a matrix, but continuous.
Right. Yeah. So whenever just in any quantum system, whenever you only have finite number of x and p's, and it's always type 1.
So type 1 to
infinity.
Yeah.
And
also, I have a question that you mentioned that relativistic QFT is type 3 to the 1.
Yeah.
And is the condition that it is local or relativity is essential to make it type 3-1 or?
Yeah. So there's one simple way to understand this type 3-1, which takes a little bit effort to explain, but let me just mention it, just this feature very quickly, is that if you look at the spectrum, say let's look at, if you look at the free field theory in the Rindler space, which I think many of us done this exercise many times, and then if you look at the spectrum, there's a frequency spectrum in terms of the Rindler time, say of a free scalar field in the Rindler space. And then you find that the spectrum in omega is supported from -infinity to +infinity.
Yes.
And this feature is closely related to the type 3-1 nature. Yeah. Yeah.
Thank you.
Yeah. Yeah. Other questions?
Sorry, I have a question.
Okay.
So if we consider lattice gauge theory with finite n or large n, so what is the type of algebra?
Yeah, so it depends how you take the large n limit. I think that's a little bit it depends on how you take the large n limit. So for example, let's consider So n equal to 4 super Yang-Mills series on the sphere.
Okay.
And so you can, so you can, let's just look at some, even just, let's just not even n equal to 4 super Yang-Mills on the sphere, just some matrix quantum mechanics, okay? And then if you take n go to infinity limits, and in principle, they can be emergent type 3-1 algebra emerges from there. Yeah, you don't even need any space. Yeah. Yeah, just even large N quantum mechanics, in principle, type 3-1 can emerge from there. Yeah.
Is there any other question? If not, let's thank the speaker again. And we will meet in 15 minutes, which is 11:05. Would it be okay for you?
Okay. Yeah.
Okay. Yeah. See you in 15 minutes. Thank you very much.
Okay. See you. Yeah.
Professor Liu,
Yes.
could I ask some more detailed question?
Sure.
Okay. I think you said that Bosonian harmonizer is a type of 1 algebra, but I think that you want to say because we can just consider the trace operation acting on some operator is already enough. But I think the one motivation is to compute the entropy of a system. But when we compute the entropy, we need to have a trace operation, and it will be relevant to the all operators of a theory. So if so, we just define the trace operation for some operators is meaningful for our goal for calculating the entropy.
Yeah, certainly. Yeah, for example, you see, say let's just take the harmonic oscillator at finite temperature, and when you calculate the partition function.
Yeah, but in a sense you should. I just say in this sense you will include the momentum and the position operator simultaneously. Then you will find the P and the X commutation relation there. So in some sense you will find the inconsistency for the trace operation.
Yeah, it just when you calculate the entropy, you don't need to use the trace of X and P. And normally to calculate the entropy, we use the
why?
Yeah, you have, yeah.
Sorry, why don't you need to use a trace? Because you have a trace is from minus beta H, and the H contains the momentum and the position operators. So in some sense, and if you do expansion, you must need to. You can always do expansion to calculate
Sure. So you will need in calculate the that trace. You will need the matrix elements, say of X or P. Yeah, that's fine. But
if you meet the matrix operation, then you meet you will meet the commutation relation between S and the P. But we know that the result gives you the minus H bar. So the trace operation, if you want to define trace operation, it does not have the cyclical properties. I mean, the trace AB does not equal to a trace BA. So in this sense, it must be type 3.
No, it's because you are looking at the you have to look at the trace class operators and the operator which have a well-defined trace, which then they satisfy trace AB equal to trace BA. Say
yes, but I think you say the AB just needed to for some operators, not necessarily to be all operators.
Yeah, that's right. Yeah.
So, but I want to ask, but my question is that when we calculate the entropy of a system, we need to concern the all operators.
No. When you calculate the entropy of the, it depends on what kind of entropy you're interested in, right? Say if you calculate the entropy, if you look at exponential minus beta H, you only need to calculate the trace of exponential minus beta H. That's well defined.
Why did you say H is well defined? H is Hamiltonian.
Exponential minus beta H is well defined.
Yeah. But it's minus beta H well defined. But if you define the trace there,
no, the trace of exponential minus beta H is well defined.
Oh, okay. Then, but why is well defined is my question? Because if you still define the trace with the cyclical relations, this means that the H cannot contain the momentum the positions simultaneously.
No, H can contain momentum and position. No, H is some operator can contain position and momentum, and the exponential minus beta H is has a well-defined trace.
Yeah, but you meet the like a PX operators.
No, you don't need X or P separately to have a trace.
Okay.
No, you don't, right? If you just do the calculation, you see you don't need, in order to calculate the trace exponential minus beta H, you don't need to use the trace of X or trace of P. You don't need to use that.
Okay. Yeah. Thank you. Yeah.
Yeah, hi everyone. So welcome back, and we will start the second session of the Professor Hong Liu. Yeah, please start.
Okay, good. Yeah, just remind you what we just discussed. So we discussed the Lagrangian limits of the operator algebra. So the key thing is that at different time, the algebra are independent of each other. Okay. So this is a fact that I will use a lot later. Now also let me say a little bit about Lagrangian limit of the Hilbert space. Because also many of the states, they also cease to have a well-defined Lagrangian limit. And so I will define states which will define the Lagrangian limit as follows. So I will define a state has a well-defined Lagrangian limit if correlation functions of single trace operators, okay, say with expectation value subtracted. So yeah, because in these states have well-defined angle to infinity limits. So of course the reason for this definition is very clear because we already defined the single trace operators, the product of single trace operators as well-defined operator in the Lagrangian limit, and then we use this single correlation of single trace operator to select the sensible states. Okay, so the sensible state in the Lagrangian limit should have so if the correlation functions of single trace operator in such a state should have a well-defined Lagrangian limit. And so let me just give you an example. One example is the thermal state, or its real-time version, which is the thermal field double states. So both states, you can show that it's a long story that the correlation functions of simple trace operators in the thermal state also have nice factorization properties in the Lagrangian limits. Okay, so they clearly survives in the Lagrangian limits. But here I want to emphasize the important fact is that in the Lagrangian limits, the left-hand side, rho beta and the TFD, they can be defined, okay, in terms the limit of thermal correlation functions. Okay, so we calculate thermal correlation functions at finite n, and then we take angle to infinite, and when we use that to define such kind of states at infinite n. Okay, so rho beta and TFD can be defined that way. And again, similar to the example of this BT I discussed before, even rho beta and TFD are well defined in Lagrangian limit. The right-hand side of those equations are no longer well defined in the Lagrangian limit. Okay, those things, for example, this trace minus beta H, the H is proportional to n. Okay, so we no longer know how to make sense of this kind of quantity. And also, this thermal field double state expressed in terms of this sum. First, this E actually also the energy goes to infinity because E is proportional to n squared for many states. And also many states themselves all those macro states, N, many of them, they don't have large N limits. Okay. So that means that in the large N limit, the right-hand side of those equations no longer makes sense. Okay, so in the large N limit, we cannot no longer talk about those equations. So this realization is actually important because this avoids many controversies, because there have been many controversies related to how to interpret this equation in terms of geometry. Say whether the thermal field double geometry, which is a black hole, should be interpreted as a superposition of many macrostate geometry, disconnected macrostate geometry. But now we know that kind of statement just don't make any sense. Because if you want to talk about geometry, you have to talk about the angle to infinity limit. You have to talk about G Newton goes to zero limits. You have to talk about the angle to infinity limit. But the angle to infinity limit, this equation no longer defines, because the right-hand side is not defined. So yeah, so this is another important message I want to convey. Just we should always talk about well-defined quantities in the angle to infinity limit, and not mix those finite n and infinite n quantities. Okay, this expression certainly makes sense at finite n, but no longer makes sense in infinite n. So we will refer to a state with a well-defined large N limit as a semi-classical state. Yeah, for obvious reasons. And for semi-classical state, then we can build a Hilbert space around it by acting finite product of symbol trace operator on it. Okay, so mathematically, this is called GNS Hilbert space. Okay, mathematically, you can show actually by acting single trace operator on such a semi-classical state, you can actually build a Hilbert space. Okay, heuristically, of course, it's easy to understand, but mathematically you can prove it exactly. Okay, using this so-called GNS procedure. So why this is so that's why this is normally called GNS Hilbert space. And so in the large N limit, then only those semi-classical states and those states in this GNS Hilbert space around them actually survive. Okay. So this means that in the large N limit, the full Hilbert space actually splits into disconnected GNS Hilbert spaces around semi-classical states. Okay, you no longer have a global Hilbert space as the finite N. Because many states in the original Hilbert space, they drop out. Okay, so in the infinite N limit, you actually have this this kind of structure. So this is also exactly what we see on the gravity side. Okay, this is the same structure we see on the gravity side. On the gravity side, we when you take G Newton go to zero limits, we define the Hilbert space where quantize a gravity field around the geometry. So to obtain the Fock space around that geometry. So for each geometry, you can construct such a Fock space. And then the different the Fock space for different geometries, they don't overlap. Okay. And so again, they form this kind of disconnect. They become superpositions of disconnected spaces. So holographic duality that large N is essentially you have this kind of semi-classical states due to some geometry on the gravity side. So by geometry, this could also be in stringent geometry. You can include alpha prime corrections, etc. Here, I'm only care about the large N. Okay, so you also can include alpha prime corrections. And then from psi, you can build the GNS Hilbert space around it. And from the geometry, you can build the Fock space around it. And then the standard identification of the states between the boundary and the block can be written as the identification of those Fock spaces, the GNS space with the Fock space. And similarly, the operator algebra of the GNS Hilbert space, then of course should be identified with operator algebra on this Fock space because it'll be identified the Hilbert space. Okay, then the operator algebra should also be identified. That means any sub-algebra in this operator algebra we always also has a counterpart sub-algebra on the right-hand side. And so let me emphasize in the leading order in large N limits, The left-hand side are generated by single trace operators, and single trace operator actually in the large N limit, they behave like a generalized free field because of the factorization of properties in the large N. Okay, so then this operator algebra for each GNS Hilbert space is generated by generalized free fields. On the right-hand side, of course, that just free fields for the gravity side in the G Newton goes zero limits. Okay, so yeah, so here is a geometric picture. Say the here there's misprint. Here should be GNS. Okay, so the GNS Hilbert space associated with some state psi 1, then it's related to the Fock space around some geometry. Okay, and then there's a disconnected, say GNS Hilbert space around some state psi 2, then associated with a Fock space around some other geometry. Yeah, the reason they're disconnected because those kind of GNS, because those states within this Fock space and the GNS Hilbert space, they contain a state with energy also differ by order 1, say from your psi. Okay, but different semi-classical states, they differ from each other by order n squared. So that's why they're disconnected. Yeah, so this is your structure of your Hilbert space. Okay.
Can I ask a question?
Yeah.
So in this picture of large and limit, can we say something about the unitarity? I mean, in a perturbative sense, in the large and limit?
Yeah. So you can talk about unitarity within each GNS space and the Fock space, and then you can no longer talk about unitarity in the global sense. So previously at finite n, you have a unitarity associated with the full Hilbert space. But now due to that somehow in the large n limits, the states between them actually they drop out. And we can no longer talk about this unitarity there's no, that kind of unitarity is lost. Yeah, this is actually the fundamental reason, essentially the fundamental reason that you have energy loss for the black hole information, etc.
In the zero temperature limit, basically we recover unitarity somehow, I believe.
Sorry?
In the zero temperature limit, I mean, in the pure ADS space, for instance.
Yeah, for the pure ADS, and then you just have the GNS Hilbert space. Again, you just have GNS Hilbert space associated with the vacuum. So you can have the unitarity associated with that factor. But then you have a GNS Hilbert space associated with some excited states. And then you have unitarity associated with that GNS Hilbert space or that Fock space. Yeah. Yeah, but not the global unitarity which relates them.
Okay.
So for example, at finite n, you have unitarity can relate your ground states, which is an empty ADS, to some black hole states. They can be related by some unitary transformation. But that kind of thing is lost when you go to infinite n.
Okay, thanks.
Yeah. Okay. Yeah, again, this kind of structure is important because now we talk when we talk about the operator algebra, we can only talk about operator algebra within each such Hilbert space. Okay. So if I call this as disjointed continent, and then you can only talk about operator algebra within each continent. Okay. And each continent will offer a representation for your operator algebra.
So I have a question about
Okay.
that slide, this slide. Here you mentioned that the operator algebra in the one-time slice could be different from the other time slice in the previous slides.
Yeah.
That is understandable in the single trace picture, but on that single trace or generalized free field is equal to the free field in the gravity side. So from the point of the free field in the gravity side, can one also understand the difference of the the operator algebra in the different time slice? Because
Good. This is a very important question, which again I will. This is a very important question, which I will emphasize later when I explicitly talk about the black hole case. Yeah, indeed, this is a key question. So in this mapping, these generalized free fields are defined for the full boundary space-time because of the feature I mentioned earlier. This single trace operate at different time, they're independent of each other. So this generalized free field actually are defined for the full space-time. But for in the bulk, those free fields, you can define them just on a single Cauchy slice. Because in the bulk, you have standard Hamiltonian evolution. And so in the bulk, you only need to specify your fields in a single Cauchy slice, and then that will determine your full space-time, the algebra in the full space-time. So you see these two dimension matches because the bulk have one more dimension than the boundary. And so here you define the free field on a single slice, but here you define generalized free field for the full space-time. So this is rather weird because when you do this mapping, a single time slice on the gravity side essentially already encodes the full space-time information on the field series side. Okay, and so this is a feature I'm going to play some role, which I'm going to discuss later. Yeah.
Okay, I still don't understand, but I will wait for the next slide, later slides.
Yeah. Okay, so now each of such
sorry, can I ask
Hilbert space or Fock space, they offer they can in principle offer a different representation of your single trace operator algebra. Sorry, was there some question?
Yes. Well, if you consider a heavy operator excitation in the boundary side, it will take you to some different geometry, right?
Yeah.
Well, does it mean we can consider mapping from one GNS Hilbert space to the another continent by heavy operator excitation?
Right. So at the finite end, that's roughly what you can do. So but at the infinite end, that heavy operator just drop out of this the operator spectrum.
Oh, I see.
Yeah.
Okay, thank you.
Yeah. Good. So yeah, so now the key is that each of such kind of continent, they offer a different representation of single trace operator algebra. And now your single trace operator algebra, the representation becomes state dependent. Okay, depend on each of these Fock space, depend on each of these semi-classical states. And so even though the single trace operator algebra or sub-algebras, they can be defined abstractly without referring any states. And so single trace operator algebra by itself is an algebra, but it's not von Neumann algebra. So as I mentioned, in defining a von Neumann algebra, you need to introduce a Hilbert space, and you need to define the weak limits in that Hilbert space. So we can abstractly define a single trace operator algebra without referring any state, but that's another von Neumann algebra. But now the representation of single trace operator algebra or sub-algebras on the GNS Hilbert space is state dependent. Okay, so on different such kind of continents and the single trace operator algebra, they can have different representations. And in particular, and now you can introduce von Neumann algebra for them now because now we have Hilbert space. And in particular, the nature of the von Neumann algebra can be different depending on the nature of the states. And so there's a trivial state dependence because we need to subtract excitation value when we define the single trace operators, say for general states. But there's a non-trivial state dependence, which is the representation of the single trace operator when they act on the GNS Hilbert space. It's actually determined by the 2-point function. So of a single trace operator in this state. And so the structure of the algebra is actually determined by 2-point functions. Okay. Yeah, so I will not go into detail here. Yeah, that's related to how you construct the GNS Hilbert space. Okay. So it is a specific representation in the states that is matched with the Bach field perturbation around the corresponding geometry. Okay. Yeah. So again, I emphasize this picture. So here you have the Bach, you have the boundary. So the boundary, the operator algebra representation depend on these states. And in the Bach, of course, the operator algebra depend on when you perturb around the geometry, will also depend on the geometry. And so both of them have some state dependence. Okay, so now let me just give you an example. So if you consider some of your double state, we have CFTR times CFTL. And then at finite n, the bounded operator algebra of CFTR or CFTL is a type 1 monomer algebra. Okay, so here we always consider the series on the sphere. Okay, so it's easier. We don't have to consider infinite volume limits. So we consider the series on the sphere, and then at the finite end, the operator algebra of CFTR just type 1 monomer algebra. And yeah. But in the larger limits, so we should consider the algebra generated by single. Say let's consider the algebra generated by single trace operators of CFTR. So we call it AR. And then the action on AR on the TFT state then form this Hilbert space. So this is the GNS Hilbert space related to HTFT. And then I will denote the MR to be the representation of this algebra on the, yeah, this, so HTFT essentially just the small perturbations around the thermal double state. It just obtained by acting single trace over the algebra. And the MR, so emphasize the MR is a representation of this this abstract single trace operator algebra in this Hilbert space. Okay, it depends on the state. For example, it depends on the temperature. Okay, so now you can argue. Okay, yeah, I would say it depends on the level of mathematical rigor you want. I can say you can show that for T smaller than Hawking-Page transition, this is actually the MR is the type 1 monomer algebra. But when T greater than Hawking-Page transition, then this single trace operator algebra, when you're acting on this thermal field double states, then actually become type 3 monomer algebra. Okay, and so so this clearly shows that the state dependence of such kinds of representations. Okay, and so this representation depends on your temperature, and temperature sufficiently low is type 1, and it's type 3. And so you show this, you can show this by looking at essentially the thermal spectral function of single trace operator. Yeah. So below the Hawking-Page transition, the spectral function have a discrete spectrum. But when you go to the above the Hawking-Page transition, another spectral function now have a continuous spectrum from minus infinity plus infinity. And then you can show that this kind of continuous spectrum from minus infinity plus infinity is actually essentially a smoking gun for this type 3 algebra. So this is one way to argue this is type 3 algebra. And then you can also use this so-called half-sided modular inclusion and translation structure, which I will briefly mention later. And also from the duality with Spark. And yeah, so this concludes my discussion, say, of this the mathematical structure, say, in the large n limits. So do you have any questions? Say, for example, yeah, on this part. Okay, good. Okay. Yeah, then now let's try to apply this kind of
Sorry, I
inside.
have a
Yeah.
one question.
Yeah.
Could I understand that your algebra is changed due to the phase transition?
Yeah.
So you think that if algebra is changed, then we must have the phase transition.
Are you asking, in order for algebra to change, whether there must be a phase transition?
Yeah.
Yeah, I think that's a good question. I suspect so. But because if you have a continuous evolution, certainly normally you don't evolve from a discrete spectrum to a continuous spectrum. You need something more dramatic. Yeah.
Okay. So I remember the Wheaton recently wrote a paper to talk about the string Breholt phase transition. I think he mentioned that he does not always find the smooth transition there. As I say, he does not always find the discrete transition or smooth transition. So sometimes they can have a smooth. So I would expect that the string Breholt phase transition may not always happen. But we should expect a string theory should be the type 1 algebra. But if we go to the Breholt state or some field theory, should be maybe for the type 2 algebra. So in this case, could I say that the phase transition may not be happen even if the algebra is changing?
Yeah. So that's a more tricky question. I think it depends on the details. I think it depends on details. You really have to look at, to decide what algebra you really have, say type 1, type 2, type 3, you really have to say.
But the string theory should be type 1.
Yeah, for the string, it's reasonable to have type 1. Yeah, that's right. Yeah.
But do you think the field theory or the Breholt theory can be type 1? I think we should expect a type 2.
Sorry, you are talking about which case? You're talking about this string and the black hole transition case?
Yes. The Breholt is also
I think I need to look at the details in that case. It could be type 2, could be type 3. I don't know. Yeah.
But maybe type 2 or type 3, but it's impossible type 1. I say for a Breholt.
Yeah, I don't know whether it's impossible to be my suspicion is that cannot be type 1, but I don't immediately say
okay.
Yeah, I have a precise mathematical.
So it's possible to have a, for example, from string to Breholt, but the algebra is still possible from type 1 to type 1.
Yeah, I'm just saying I don't have a proof that this can happen or this cannot happen. I suspect that the algebra may change, but I don't know the answer. Yeah. I have a suspicion, but I don't have the exact answer.
When we say Breholt, it should be some classical Breholt. So I speculate. And then we say type 1 is for the quantum gravity. So it's why I think from my intuition or physical picture, it's hard to say Breholt case can correspond to the type 1.
Yeah, I agree with this intuition. Yeah, I agree with this intuition, but I just say I don't know.
Okay.
Yeah.
Thank you.
Okay, so now let me try to apply those insights which we obtained in the larger limit, and then to understanding this emergent time and the horizon in the internal black hole. So again, this is the Penrose diagram for internal black hole in ADS. And just remind you the questions is that we are interested in the boundary description of the future and the past region. We would like to understand how does the Kruskal time emerges from the boundary theory. We would like to understand the boundary descriptions of the horizon and associated with causal structure. Okay, so we So first, again, just this is I just said for the when you above the Hawking page transition. Okay, so we expect this AR on the Hilbert space, on the JS Hilbert space, and you can also similarly define the ML algebra, single trace orbital algebra, associated with the left CFT, and the claim is that they should be the type 1 or type 3 volume management. And so so now let's try to see how this maps to the Bach picture. So in the Bach, we just quantize the gravity field around the black hole, and then you get the Fock space, and then you build the Hawking, you build the Fock space on this Hawking vacuum, and then you can also have the operator algebra in the right region. Or yeah, you can have the operator algebra in the right or left region of the black hole, which I called M tilde L and F tilde R. And so these are the Bach operator algebras, say in the right and left regions. Okay. So they can be defined on a single Cauchy slice. Okay. And then the duality, the standard duality for the black hole, for the internal black hole, which we are familiar with, can be written in this language as that we identify the GNS Hilbert space around the thermal field double states with the black hole Fock space. Okay, and then this Hawking vacuum then is identified with this this vacuum on the GNS Hilbert space side. So this vacuum on the GNS Hilbert space side is just essentially corresponding to the original thermal field double states. So the original thermal field, because the GNS Hilbert space is obtained by your acting single trace operator on the thermal field double states, and so the vacuum in the GNS Hilbert just represents your original thermal field double states. And then we identify the algebra. So the single trace operator algebra for the right theory then is identified with the field operator in the right region, and the ML is identified with MA tilde. Okay, so this is the standard, the dictionary to identify the operators and the field in the Bach and the boundary. Good. And now, so this M tilde R and M tilde R L. So in the Bach, when you take G Newton goes to zero limit, which is an RGN limit in the boundary theory, essentially you have a quantum field theory in the curved space-time. And this M tilde R and M tilde L, they're just some kind of operator algebra in some kind of local region in this Bach space-time. And from what I mentioned earlier, say if you have a local operator algebra in the quantum field theory, you always is the type 3 one. So this matches with the claim that this MR and ML should be type 3 one. Okay, so this is what I mentioned, the Bach confirmation that this claim, the Bach support of this claim that MR and ML become type 3 one in the larger entities.
I have a question in here, Hilbert
Yeah.
space. So here, Hilbert space in the bulk side, you probably consider some fixed background, and there you consider some metal field on the fixed background, right? So does it also include some like a gravity also, graviton, like a fluctuation?
Yeah, everything, yeah.
Everything. So here, when you say the operator algebra, does it mean then if you include the graviton, does it have like a local operator, or do you have to take some like a gauge invariance, some physical operator in the bulk? Or?
Right, indeed. When you involve the graviton, it's a little bit tricky. So you have to be careful about the gauge constraint, etc. So the simplest way to do it is you fix some gauge, and then you can just talk about this algebra of graviton. As far as if you only ask gauge invariant questions, and then it's okay. Yeah.
So also, should it be also local operator? Like when you say operator algebra, does it only restrict to some local operator, or it's supposed to be any like a non-local operator?
Yeah, so here it can be non-local. We just only operator have to be restricted to the R region. Yeah, it can be non-local within the R region, but it has to be localized within the R region.
Okay, thank you.
Yeah, by local we just means that localized within this region, but within this region can be non-local. Okay, yeah. So so now let me emphasize one point. When we make this identification, MR and MR tilde and ML and ML tilde, this only identify the algebra with the algebra outside the horizon. This identification itself does not tell us the global structure of the space-time. In particular, whether the left theory and the right theory are connected or not. Okay, so this identification does not say touch this question at all. Okay, so we just identify some algebra in some, yeah, yeah, we just identify with some Bach algebra. So our goal is just to understand whether this right theory and left theory are actually connected. Okay, to get this full black hole structure. Okay, so that's corresponding to this F and P regions have to emerge from this picture. Okay. So again, let me remind you this picture that the algebra of single trace operator, they're equivalent on they're inequivalent on different Cauchy slices. Okay. And so that means MR and ML are defined on the full boundary space-time. So if you have a quantum field theory, ordinary quantum field theory, you define the operator algebra on a single time slice. But because of this feature, so MR and ML actually are now defined on the full boundary space-time. So this is related to what I said earlier. So this identification of the algebras is actually a little bit peculiar because MR, yeah, so this is just a rough picture of the boundary space-time. So the vertical direction is time, horizontal direction is space, okay. So the MR is defined in your full space-time. Similarly, ML is defined in your full space-time, boundary space-time. But in the Bach, the Cauchy slide, the ML tilde and the MR tilde are defined on a single Cauchy slide. So this identification is actually rather funny because this is the full space-time algebra, okay, including already the full time evolution on the boundary is mapped to a single time slice in the Bach, okay. So that's by itself just tell you the Bach time and the boundary time, they're not simply related. Okay, they're not simply related. So then how should we understand the times in the Bach gravity? Okay, so let's imagine you have a Cauchy slice t equal to 0 and evolve to some other time. So this is the Kruskal time. Okay, suppose you evolve to some other time. So as I said, in the Bach, we have essentially a quantum field theory in the curved space-time. You have a Hamiltonian evolution. So the operator on this new slice is equivalent to the operator on t equal to 0 slice. Okay, so they are equivalent. Okay, so this evolution from the algebraic point of view is just like an automorphism of the algebra itself. Okay, it's a mapping of algebra. Yeah, so the mapping between the algebra t equal to 0 to this slice is like automorphism of the algebra. So from this picture, the Bach time evolution, when we translate into the boundary point of view, the boundary, the operator algebra, the single time slice just translates into the union of the MR and ML. Okay, so that means that the Bach time evolution just corresponding to the boundary automorphisms of this algebra. Okay, so it's not any kind of automorphisms. Okay, yeah, because the algebra in principle have many automorphisms. And not any automorphism, somehow have to be that kind of automorphism which give you a notion of time. Okay, have to give you a notion of time. So this is our task. Is now we translate this question of finding the times in the gravity side into finding some boundary automorphisms, which we may interpret as some kind of time evolution. So this is the question I already mentioned. So now let's talk about the obvious boundary automorphisms. Okay. So one is the obvious one we often consider. Is just if the Hamiltonian, if I denote the Hamiltonian for the right series to be HR and the left series to be HL, so it's HR minus HL. Okay, so HR minus HL, they evolve using the standard Schwarzschild evolution. For the right slice, they evolve forward in time, and the left slice they evolve backward in time, but it's always outside the horizon. Okay, this is like a Windler kind of evolution. It's always outside the horizon. So here I want to emphasize is that even though HR is not well defined in the large N limit, and HL is not well defined in large N limit, but the HR evolution defined by HR minus HL is actually well defined in the large N limit, because this corresponding to the modular evolution, and the modular evolution actually survives in the large N limit. Okay, so this evolution actually survives in the large N limit. But now, if you we often consider evolution is that you evolve by HR plus HL. But actually, there are lots of misconceptions associated with it. It's because the HR and the plus HL, the evolution generated by this operator, is actually not well defined in the large N limit. Okay, so this actually this evolution based on this is not well defined. In fact, the evolution based on any linear combination of HR plus HL, other than HR minus HL, are not defined. I don't have n go to infinity limit. So this can also be seen on the gravity side. If you naively apply the evolution generated by HR and HL to the time slice in the bulk, which you can do, because we have the map between the boundary and the bulk, okay? And then you find the generate flow like this. Again, only take you outside the horizon. And but this evolution is not smooth. There's a kink at the horizon. Okay, there's a kink at the horizon. So this is just a reflection of somehow this is actually not well defined in the large N. But if we want to consider this kind of evolution, this kind of Kruskal evolution, which can take you behind the horizon, okay, to this kind of Cauchy slice behind the horizon, this cannot be achieved using any combination of HR plus HL, which I mentioned here. Okay, any combination of HR HL, there's no way can take you behind the horizon. Okay, just by definition, they only evolve evolution outside the horizon. So this kind of evolution must be emergent. Okay, cannot be any other standard ones. In particular, for Kruskal-like evolution like this, the generator must involve non-trivial couplings between CFTR and CFTL. So whatever generator to generate this Kruskal evolution must involve both CFTR and CFTL. Why? It's because once you cross the horizon, then this operator, once say you take an operator start from here, once take it behind the horizon, and then you will be causally connected with both left and the right. If it's causally connected with both left and right, then they have non-trivial commutator with left and right. Okay, and this generator then must involve both non-trivial couplings, CFTR and CFTL. This kind of linear superposition of HR plus HL just won't do it. Okay. So now the question is, how do we find this? Okay, the question, how do we find this? So it turns out this actually can come from this emergent type 3-1 structure. Okay, so this gives rise to the emergent times, sharp horizons, interiors, associated causal structure, etc. So and for this, to do this, we have to use a very special structure specific only to type 3-1, which does not exist for any other type of von Neumann algebras. And this is, before let me just emphasize that somehow this type 3 algebra will make it to have this kind of emergent horizon and the future and the past region. But on the other hand, if you are below the Hawking page temperature, and then those algebras remain type 1, okay, all those algebras then it's type 1 in that case. And then essentially we have a discrete picture. And then these two parts actually they're disconnected. Okay. And the big, so this M tilde R and M tilde L, they're also type 1. And now they become the full algebra in this disconnected spacetime, and then automatically type 1. Okay. So due to the special structure of the type 3-1, and then you get this kind of connected structure in the block. So now let me explain where does this special structure for type 3-1 come from. So before I do that, do you have any questions?
I got a question.
Okay.
So the Kruskal-like time evolution, you said that there should be a coupling between R and L side.
Right.
And so basically, where we are changing in the boundary side, we are changing Hamiltonian such that we can introduce a coupling between R and L side. That is basically what we are doing here.
Yeah, you have to ask the question. You have to ask the question. You can have a, say, you can consider a theory, say we just non-coupled between safety L and safety R. You can evolve it, say at finite n by HR plus HL or some other, any combination of HR plus HL. But the claim is that any that kind of evolution will not lead to the Bach evolution. If you want to describe the Bach evolution, you must use some kind of generator which couple the safety L and the safety L in a non-trivial way.
Oh, okay, I got it.
Yeah.
Thanks.
Right.
I have a question, similar question. So let's say you have some operator which generate this Kruskal-like evolution.
Yeah.
And that you have that operator, and then if you take a finite n, like can you take a finite n on that generator, and what happened there? Do they still have a left
so we
right
don't know the answer because as you will see, that generator is intrinsic to this type 3-1 structure. And this type 3-1 structure is intrinsically large n. It's only emergent in a large n limit. At finite n, this type 3-1 structure does not exist. So I suspect the story is like a little bit like a phase transition. So remember in the standard story of the phase transition, say in statistical physics, the phase transition, strictly speaking, only exists in the thermodynamic limit. Okay, you have to take a limit to get the discontinuity in the phase transition. But of course, in real life, you are never in the thermodynamic limit. It's always finite number degrees freedom. You have many degrees freedom, but it's always finite. It's never the exact thermodynamic limit. But of course, we observe sharp phase transition. So I suspect the structure of this evolution operator and some structure of this type 3-1 structure will remain in the finite n. But as in the phase transition story, it just to describe that we have to use some different language. Yeah. We can no longer use this language because this language is strictly a large n language.
I see. Okay, thank you.
Yeah. Right now we don't have that kind of language at the finite n. Yeah.
Well, can I ask a question?
Yeah.
I'm a bit confused with this kind of story with type 3 and type 1.
Yeah.
So in this figure, do you mean these black dots in the lower figure represents finite degrees of freedom, which is represented by type 1 polynomial algebra. What do you
Yeah,
mean
that's
by
right. Yeah, that's right. Essentially, you have some excited states. So this EFT is some kind of, yeah. So here is the thermal field double between some excited states between each discrete geometry. Yeah, between each separate geometry. Yeah.
And why in the upper right figure this implies type 3?
Oh, no. What I want to, yeah, this is just the outline of the result. It just say we can show that for t greater than THP, the algebra is type 3(1), and then we can show that type 3(1) algebra will lead to this structure.
Oh, I see. And how is type 3 related to the emergent time?
Yeah. That's what I'm going to explain. Here, I just tell you the. Here, I'm just trying to tell you the picture I'm trying to get, so that you know what I. So that you know the goal. Yeah.
Okay. Thanks.
Yeah. Here, just summarize the general picture we get. Yeah. Okay. Good. So here, now it turns out for type 3(1) structure, type 3(1) monomer algebra, there's a very special structure, unique to type 3(1) monomer algebra. So here I have to use a little bit of mathematical language. It's just simpler. So suppose that M is a monomer algebra, okay, and then the vector, then you have a vector omega, which is cyclic and separating for M. So in the case of the black hole, you can just take this M to be MR, and then this omega is either the Hart-Hawking vacuum or just the GNS vacuum, which they identified, okay? And the cyclic and separating just means that the any operator, say, if you act operators from M on these states, and the resulting states are, say, the dense in your Hilbert space, right, in your GNS Hilbert space. And separating means they never annihilate these states. Anyway, so this is a mathematical condition which is satisfied, okay, by this type 3(1) algebra we talk about. And now, if you can find another von Neumann sub-algebra, the sub-algebra of M, okay, we call N, with the following property, is that omega is also cyclic for M, means that if you act operator on this Hart-Hawking vacuum state, it's still, you generate the full Hilbert, it's still dense in your Hilbert space. And further, if you act the modular flow generated by M, so for each algebra, there's associated modular flow. So if you use the modular flow of M acting on the sub-algebra, for half of the time, for t smaller than this t, in principle, you can take to minus infinity to plus infinity. But for t smaller than 0, it takes the algebra operator N to itself. Okay. So if there is, say, von Neumann sub-algebra of M satisfy these two conditions, and then there's a powerful theorem, okay, tells you that there actually exists a unitary group US with the following property, that this US is generated by some operator G, that G is bounded from below, okay, and also this leaves this vacuum invariant. Okay. This evolution leaves the vacuum invariant. Okay, so this condition is key. Okay, so remember, so if you think about in quantum mechanics, how do we distinguish time evolution from a spatial translation or some internal unitary transformations? Unitary transformation corresponding to some internal symmetries. Is that the generator for the Hamiltonian is bounded from below? Okay, and the spatial translation is not. Okay, P is not bounded on either side. Okay, and the generator for some internal symmetry is also a general will have both sides. Okay, so this essentially tells you that this S is an emergent time. Okay, can be interpreted as an emergent time. So now finding such a sub-algebra then give you a new emergent time. And this structure only exists for type 3-1 algebras, okay, which is proved by Borchers. Yeah. So now let me give you a simple example. So let's just consider again the Rindler story. Let's consider the operator algebra in the right region. Okay, shaded by this orange color. You call this orange, yeah. This orange color. Okay, so this M. So let's take this M to be the operator algebra in the right region, just for this whole region. And now let's consider the sub-algebra corresponding to in this right region, just shifted along the along this x minus direction. Okay, again, this is infinite wedge algebra for n. So this n, yeah, just from the Schneider theorem, n is also cyclic with respect to the vacuum. Okay, m is cyclic separating with respect to the vacuum, and n is the same thing. Okay, and now the modular flow generated by the algebra of M is essentially the boost for the Rindler case. So now immediately we can see, yeah, if we take omega to the Minkowski vacuum, and then under the boost, the half of the boost which N will go to itself. Okay, the boost is just the shift the if you just imagine how the boost works, and half for boost in one direction will take n going into that direction, but the other boost will take n go to this direction, just take to itself. So that means in this case there exists such a G bounded from below, okay, corresponding we generate such a unitary transformation. Of course, in this case, you may guess what is this US. So this US is just the translation, actually just translation. G just generate translation along the x minus direction. So of course, this is just what we normally call the light cone Hamiltonian. Of course, this is bounded from. So in this case, give us a familiar example, which is just the light cone Hamiltonian. And similarly, you can do some other a choice of n, and then can give you the other. So this is corresponding to, say, h plus p. You can also get h minus p by taking some other sub-algebras. So now the key is that now if you look at how this translate so this just generates a null translation. So now if you look at how this null translation acting on M. Okay, so so when s smaller than 0, you take, this is just a null translation. So if you translate in this direction, you just take M into itself. Okay, and in particular can take M to n. Okay, it just translates in this x minus direction, in the negative x minus direction. So for s smaller than 0. But for s greater than 0, you just translate this M into now the future region. Okay, so essentially now using s greater than 0, you can just generate the future and the past regions from the algebra of the right and the L regions. So essentially using this structure, if I only know the algebra in the right and the L regions for the Rindler spacetime, I can actually generate the full Minkowski spacetime. Okay. Starting with the Rindler L, and now we can actually obtain the full. And then we can actually obtain the Minkowski time. Okay, because you already, if you have x minus and x plus, and then of course you do a linear combination of them, you can just generate the x0. So from this R and the L point of view, this night cone time and the Minkowski time, they are emergent time from this half-sided modular translation structure. Okay. And now to do the black hole case, we just need to find the appropriate sub-algebra to sub-algebra of MR to do the similar thing. Okay, so now this parallel with Windler is very clear. So because of the right and L region of the Schwarzschild black hole is just like some kind of Windler. And now essentially we want to find the similar structure so that can recover us the full Kruskal spacetime. Okay. So I'm seeing I'm already 1 hour now. So do you want me to continue a little bit, or I can continue tomorrow? Yeah.
You can continue as you wish. Yeah, we still have time.
Okay. Yeah. Let me just continue a little bit. Yeah. So that I can reach a point. So now, yeah. So now using this US, we can just try to generate this full spacetime. Okay. And so this US, yes, I will show that this US, you can construct US, and this leads to emergent time. Actually, there's an infinite number of such times. Okay. So here, let me just mention one thing. So where theorems of half-sided modular translations ensure existence of a US, and finding it explicitly in general is very difficult. Okay. But in the larger limits, the algebra of single trace operators in this GNS Hilbert space can actually be described by generalized free field theory. So in this case, we can actually work out this US explicitly. Okay. In this case, we can actually work out the explicit expression for US to a universal form up to a phase factor, which depend on specific operators and algebras. So essentially, we can actually work out this US, okay, for whatever sub-algebras. They always have a universal form. Then up to this phase factor, and this phase factor will depend on specific algebra, okay? Specific sub-algebra and specific operator you are talking about. So now let's consider one example. Let's take this N to be the sub-algebra, because so suppose this is the boundary space-time, this is the spatial direction, this is the time direction. Okay, so we can take the boundary to be a circle. Say for simplicity, we can see the 1 + 1 dimension theory. So now let's take this under the M is the full algebra of the boundary theory, single trace over the algebra. And now let's take the N to be the sub-algebra, which corresponding to T smaller than 0. Okay. So again, this is intrinsically types Nagian limit, because as I mentioned, at the finite N, the operator algebra is equivalent to at any Cauchy slice. So at the finite N, then this N will be the same as the M algebra, because they're all equivalent just to a single Cauchy slice. But now at the infinite N, the different Cauchy slices are inequivalent. So this N is actually a proper sub-algebra of N. Okay, so N is now a proper sub-algebra. So, and now you can show that this N actually satisfies all the conditions of this half-sided modular story. Say, for example, here the modular flow just associated with M is just time translation. So when you do a time translation in the lective T direction, of course, you evolve N to itself. So now with this choice of N, we just need to find the appropriate, we need to find the US associated with this N. So as I said, at the generalized free field level, we can actually determine this US as up to a phase factor. But finding this phase factor is actually not easy. Okay, because this is strongly coupled problem. Yeah, because we are looking at strongly coupled limit of the N equal to 4 super Yang C. Sorry, anybody has a question? Does someone have a question?
I have a question.
Okay.
So how unique is the G, positive G for a given theory?
Sorry, how
unique
is G?
Yeah, G.
Yeah,
where
this
U is e to the
this G.
minus
Yeah.
GS.
Yeah, so this G is unique for each choice of n. So G is unique for each choice of n. But I will show actually there's an infinite number of choice of n you can do.
So, I mean I see. Then how the the horizon can be identified in terms of
Yeah.
operator.
That I will need to talk about later. Yeah.
Ah, I see.
Yeah, that will come.
Okay.
Yeah, so the claim is that this n will generate a new time for you. Okay. So now we have to find the phase factor associated with this n. We have to find this US associated with this evolution. Okay. So once n is fixed, then this US is fixed, that G is fixed. Okay. So, but finding this US is actually a strongly coupled problem we cannot directly solve. But then we find a trick to do it. Is we argue, we can actually in this case we can essentially show that the operator algebra in n is actually equivalent to the Bach operator algebra in this n tilde region. So now just so n covers the half space-time of the boundary. Now imagine just draw a light cone at t equal to 0 point to the Bach in the Bach, and then just look at the causal value of this n region. Okay, and we call it n tilde. So the claim is that the Bach field or algebra in the n tilde region is equivalent to the n. So based on this equivalence, then this phase factor for US then can be translated into phase factor for this n tilde, because now they're the same algebra. But now in the Bach, we have a free field series. So we can actually calculate this free field series. So it turns out that this phase factor, which undetermined for this US, is given by the phase shift at the horizon. Okay, so yeah, let me just explain this a little bit. So if you look at the scalar fields, so now let's look at how this US acting on the scalar fields. So let me just emphasize one point. Yes, I'm saying that the action of US on the fields, say on the operator, then can be reduced to a phase factor. This phase factor, of course, will depend on which operator you have and depend on which sub-algebra you have exactly your choice of n. Okay. So it turns out when you act on the scalar, this phase factor is just given by the phase shift of the scalar at the horizon. Okay, so for those who are familiar with the behavior of a scalar field in the black hole geometry, say if you quantize a scalar field, solve the wave function for scalar field in the black hole geometry, and in the horizon you have an incoming wave, and you have an outgoing wave. Okay, and then if you impose normalizable condition at infinity, and then that will generate a phase shift between the incoming wave and the outgoing wave. And this precisely that phase shift which go into this US. Okay, which go into this US. Anyway, so now you can just fully determine this US, and now you can just see how it acts on the you can just work out this US explicitly. For example, in the example of BTZ, we can just work out the explicit of action of this US. So today it's a little bit late, so maybe I should stop here.
Yes. Is it okay to stop here? Then then
so the tomorrow I will explain how this US can be used to we can then you can work out explicitly take operate in the Bach and how US act on it, and you see the signature of the horizon, the signature of the future regions, etc.
Sure. It will be great to continue tomorrow. Then thank you for the
because
great.
Today will take a lot of time to do that whole story. I'm going much slower than I planned. Mm-hmm.
Okay, thank you very much for the clear the lecture. Please ask a question. in online and offline?
Sorry?
Yeah, I mean, I asked the question. Yeah, there is one question.
Okay.
So you said for type 3-1, so there exists a unitary group US.
Yeah.
And so does such a unitary group exist for type 3-0 or type 2?
No, it only exists for the type 3-1.
Type 3-1 only.
Yeah. Yeah, that is the statement proved by Borchers. Yeah. Yeah, have to do with the spectrum condition I mentioned earlier. That type 3-1 have this continuous spectrum from minus infinity to plus infinity. And that turns out to be very, that's important for this,
Thank you.
Any other question? Actually, I have a very naive question. Probably, in the 3D case, people also talk about this multipartite entanglement and some like a multi-wormhole like a solution, like Balasubramanian or these people in the past studied such kind of. I'm not sure it's really one can study in the holographically, but they also showed some like multiply connected 3D black hole.
Yeah.
So in that case, can you also work out this kind of thing? Do you expect that also somehow you have some similar story there, or?
Right. I think one problem with that kind of wormhole is that they don't have I need to remind myself what was the story there, but the only issue is whether you have you have an analog of the TFD states or not. So if you have an analog of the TFD states, and if that states have a well-defined Lagrangian limit, and then in principle you can carry out this story.
Okay, thank you.
Yeah.
So any other question in the online? If not, let's thank speaker again.
Okay, yeah, thank you. Yeah.
Welcome back, everyone. Now we will start the second session of the Friday workshop. And the second speaker is Professor Hong Liu from MIT. He will give a third lecture on the emergence of space and time in holography. Please welcome him.
Okay, yeah, good. So let me first just started by reminding you where we stopped yesterday. So yeah, maybe I will go to actually an earlier slide. So we have this picture that actually I missed that slide. Yeah, we have this picture that we have this identification of the block of the boundary algebra, single trace algebra in the right region, then should be in the right CFT, then should be identified with the Bach field algebra in the right region outside the horizon. Similarly, for the single trace operator algebra for the left CFT to be identified with the operator algebra in the left. And then now here you have two situations. One is for T greater than the Hawking page temperature, then you have a type 3-1. And then and in this case, we want to show that this full black hole spacetime emerges, including the horizon and the future and the past region. And so mentioned by passing, when you have the T smaller than Hawking page transition, and then you just have the type 1. And in this case, you just get two disjoint geometry. And so the key to reconstruct the black hole space-time is that this type 3-1 algebra has a very specific structure called this half-sided modular translation. And if you find, say, if you can find a sub-algebra, say, of this MR, which satisfies certain properties, and then that's from a theorem by Borchers, then that implies the existence, say, of an emergent time. Okay, so that's the basic idea. Okay, and so the sub-algebra we are going to choose is this so this MR is the full algebra. It is the single trace algebra defined for the full, say, CFT, right? And now we take the sub-algebra to be the single trace operator, say, below t equal to 0. Okay, so including all the single trace operator with t smaller than 0. And so and then you can show that this sub-algebra satisfies all the conditions for this half-sided modular inclusion. Then that would imply you will have emergent time associated with choice of sub-algebra. And so I mentioned that that you can actually, for the generalized free field, which is the larger n limit, you can actually find this transformation US explicitly up to a phase. And but finding this phase is a Schoening-Hubbard problem, which we cannot do directly in the Yang-Mills theory. And for that purpose, we have to use a trick to find the algebra equivalent to this algebra n in the bulk. And so this is the claimed algebra in the bulk. And then we can use this algebra in the bulk to find this phase. Okay. And so that's the basic idea. Okay. And so now you can just work out.
Can I ask one question?
Yes.
Probably you explained yesterday, but let me can you remind me that when you choose the sub-algebra and then this time, emergent time is uniquely determined, or emergent time or emergent time slice is uniquely defined, or there could be some other like possible.
Yeah. So when you, for any specific choice of n, satisfy this half-sided modular inclusion condition, and then this US is fixed. This US is fixed, and so from this US we can we interpret the action of the US as the time evolution, this emergent time evolution. And if you can choose a different n, as I'm going to mention other choice of n, and then you will get a different US, and that's corresponding to a different choice of time. And actually, we will see there's an infinite number of such choices.
And this operator algebra is not on the time slice, but in the also here previously you talk about this operator algebra, you consider the time slice, and you talk about this operator algebra. But here, when you say sub-algebra n, it's defined in the time also, like in the time interval.
Yeah, so this is the boundary. This is the boundary theory, right? We start from this boundary theory, and which the operators are defined for the full space-time. And then we look at the sub-algebra, and then from the boundary point of view, the sub-algebra implies is automorphism for the full algebra. And this automorphism, when you interpret language, becomes the time in the bulk.
Okay, thank you.
Good. So that's the point that I emphasized earlier, is that in the boundary theory, the operators actually are defined already for the full space-time. The time is already there. The boundary time is already, you already have the information about the boundary time. And but somehow by choosing some sub-algebra, you generate some automorphisms, And those automorphisms then is interpreted as the time evolution in the block. Yeah, so in the case of BTZ, you can actually work out this procedure very explicitly. Everything can be worked out in closed form. Say for scalar fields, we didn't try for more complicated tensor fields. So for scalar field, everything can be worked out very explicitly. And so let me just tell you the answer, another detail. And so let's look at, say, an operator, say a box scalar field in the right region, okay? And then yeah, so let me just emphasize this picture. So this operator phi, say phi x as this scalar field evaluated at some point in the right region. So this is the then this is the element of this m tilde r I defined. So this is the element of the Bach algebra. And also from the ADS-CFT dictionary, this is the this m tilde r is equivalent to the single trace operator algebra in the boundary theory. And then this phi can also be treated as a boundary operator. Okay. And so more explicitly, say if you just expand do the standard mode expansion for this phi for the threshold right region, and then A and A dagger in the mode expansion can also be interpreted as the creation and annihilation operator of the generalized free field for the boundary theory. Okay. And yeah, so this way, this phi x can be just treated as a boundary operator. And this US is also just a boundary. It's an automorphism which we generated from the boundary. Okay. And now by acting this US on this operator in the Bach on the point, and then we get some new operator. And now we want to interpret this new operator as, say, in some future time from the Bach perspective. Okay. Good. So if you do this, say, of course, S equal to 0 is just identity map. And now you can take S either to be positive or negative, etc. So now it turns out, so if you, for positive choice of S, and then there is a non-vanishing value S0 greater than 0, and something interesting happened. So for S smaller than S0, so this phi x is a field in the right region, okay? So by definition, this is an element in the CFTR, as I mentioned earlier. Okay. So for S smaller than S0, you find that this evolved operator still remains in the CFTR. But then when S greater than S0, so there's a sharp transition. So at S equal to 0, for S greater than S0, then in this evolution, then the operator in the left CFT is generated from this evolution. Okay. Geometrically, this is precisely what you expect from when you take an operator across the horizon. Okay, so let's imagine, say, let's take an operator in the right. Okay, this phi x initially some point in the right region, and then this belongs to the CFTR. And now once it crosses the horizon, so suppose say this evolution takes you behind the horizon, and once you cross the horizon, and then this operator becomes causally connected to the left region. Since it's causally connected with the left region, then its commutator with some left operator become non-zero. So that means that this evolved operator must involve some element of CFTL. Okay, so that's what you expect should happen when you take an operator behind the horizon. And so this is exactly what we see here when you act this US on this phi x. Okay, so you find that there's a sharp value of S0, and then CFTL is generated. And so we can view this as a signature of a sharp horizon. So I want to emphasize that this is actually a highly unusual feature. So for example, if you take the standard quantum mechanical system, say whose algebra, say, is type 1 Modular algebra, you can prove that this never happened. Okay, so if you have the standard type 1 modular algebra, what happens is that either when you evolve, if you take some US, what happens is that either, say, for all value of S, say this evolved operator always in the CFTR, or whenever S become non-zero, and then CFTL is generated. Okay, so here is a highly non-trivial thing. Is that there's a finite value of S0 greater than 0. There's a finite range of S. So this phi remains in the CFTR. Okay.
Pong,
Yes.
can I ask you a question? I mean, the CFTR and the CFTR times CFTL has a different dimensionality, right?
The different what?
Dimension. Hilbert space has different dimension.
Yeah.
Right. So how phi can evolve from one Hilbert space into a bigger Hilbert space?
Oh, so you always view the phi. There's a slightly rotation issue here. When I say phi belongs to CFTR, means that this is an operator in the CFTR tensor identity operator of CFTL. Yeah, so you always view this operator as an operator of the full the CFT tensor CFTL. Just at the beginning, the CFTL part is just identity.
So, but anyway, it should be pure state, right? After evolution, if it exists.
Sorry?
It should be pure state if it evolved.
Yeah, here we are evolving just an operator, or we're not evolving a wave function, we are evolving an operator.
Right. Okay, thank you.
Yeah. Yeah, so so heuristically, so in order for this to happen, okay, this US must involve non-trivially both, say, operators of CFTL and the CFTR. So the unusual thing again is I want to emphasize is this finite range of S0. Say if you imagine this US, say it's generated by some simple superposition, say HR plus HL, and then you will always remain in the CFTR. Okay, because by definition HL commutes with phi, and so you will always remain in the CFTR. But normally, if you include, say, US to be some non-trivial coupled, generated by some operator non-trivially coupled between CFTL and the CFTR, and then for any S non-zero, and the CFTL will be generated. And so the non-trivial thing is this finite S0. So in fact, we can use the this behavior is just purely a field theoretical behavior. Okay. Just some quantum mechanical system. So we can actually view this, say for any quantum system, you can say you can ask the question whether something like this can happen. And we can say for any two quantum systems, if such US and S0 exist, and we say they're causally connected, in the sense that if they have some kind of gravity dual, then this gravity dual must have a horizon separating them. And
Hi, I have a question. If we
Yes.
if we consider type 2 and type 3 from algebra, then we should not have the pure state. How do I understand this thing in this figure or this BTD state?
Sorry, say it again.
If I consider type 2 and type 3 from my algebra, then I do not have the pure state. Then how do I understand this thing for this example?
No, here we are just involving operators. We are not involving states.
So I assume that now the state should be, if I say a state for this BTD, I should assume that this state is not the pure state.
No, the state is just, the state of the system is always just thermal field double state. No,
So
sum
the-
of your double states is we work in the Hilbert space of this GNS Hilbert space generated around this So the Hilbert space is the GNS Hilbert space around the sum of your double states. And now we look at the operators in that quantum system, and we evolve that operator. Yeah.
So then I think that maybe your paper or Witten's paper said if the algebra is type 2 and type 3, they will know the notation of the pure state. What does the mean exactly?
Here, that question is not relevant here. Here, the phi x is just some element of some type 3-1 algebra. And the US is some feature of this type 3 algebra. We just talk about this evolution of the operator. We're not talking about any state or talking about any
Okay, maybe okay. I make it some point. Thank you.
Good. So now we can ask what does the value of this S0 mean? Okay. And so here, if you just do the calculation, you find some S0. Okay, so now you say, now let's ask whether this S0 have any, say, geometric meaning or any physical meaning. So again, so this is a quite a thing we are looking at. And it turns out, let's imagine we use Kruskal coordinate to describe this X. Okay, so the initial value of X is given by some Kruskal value U0 and V0. And turns out this S0 is precisely equal to the minus value of the U0. Just remember in the right region, the U is actually negative. Okay. So this S0 is exactly the distance in Kruskal coordinates to transport this point to the horizon, okay, along this U direction. It's like you are making a U translation, okay, along the U direction. And so I emphasize when we define this phi x, there's no Kruskal coordinate used. Okay, this is just evolution of this operator, and it just turned out somehow this S0 can be interpreted in terms of Kruskal coordinates. And in particular, if S is if your initial point is very close to the horizon, it turns out that this transformation is actually local. And so this transformed operator is precisely, so this transformation is precisely corresponding to you just translate this operator by distance S along the U direction. Okay, just the Kruskal law translation along the U direction when X is close to the horizon. But for the general value of X, the transformation is actually non-local. Okay, it does not correspond to a point-wise transformation. But nevertheless, it respects the causal structure in the sense that somehow this S0, even though the transformation on X is non-local, but there's this sharp value of this S0 given by minus U0, and then you start crossing the horizon. And in fact, you can explore the causal structure a little bit.
Can I ask a question?
Sure.
I'm a bit confused. So what was the original definition of US?
Sorry?
What was the original definition of US?
US is just some operator you can define, say, in the boundary theory. I didn't give you the explicit derivation of US. So in the paper, we worked out how US act on the field explicitly. So you can just apply that thing mechanically. Yeah.
Okay. If I remember correctly, yesterday I think you said US generates the X minus translation, and here it seems that the X minus translation only holds for the region near horizon. Is it correct?
No. So so when I say the X minus transformation, that's corresponding to the ADS, that's corresponding to the standard Rindler story, to Rindler in Minkowski spacetime.
Mm-hmm.
So
I
there,
see. Uh-huh.
so there, yeah, that's just a toy example.
Oh, okay,
which,
okay.
Yeah, that's a toy example, but there US is just exactly just not X minus transformation, X minus translation everywhere.
I see. Thank you.
But here is a much more complicated situation. This is the ADS Schwarzschild black hole. Yeah. Good. Yeah. So for the ADS Schwarzschild black hole, for BTZ, we can work out the action of US. Say with some efforts and some tricks, etc., mathematical tricks, we can actually work out their action on the scalar field explicitly, which I'm not describing here. There are lots of details there. Yeah, it's actually rather non-trivial. Yeah, there are some tricks we need to do in order to find the action. I'm just telling you the result now. Okay. Good. And you can explore this problem. You can explore this issue a little bit deeper. So let's just imagine you take some initial point x1 from the right region. Okay, so take the operator in the right region. Yeah, again, this is the U and the V. This is a black hole space-time, which I now draw in terms of Kruskal coordinate. Suppress the boundary and the singularity. Just say I just draw in terms of Kruskal axis, and those dashed lines are the horizons. So now let's imagine we start the initial point xy in the right region, and then act this US. Okay. And then let's look at another operator by L in the right, in the left region, and it sits at point x2. So now if you evolve this right operator using this U, and then the evolution, as I mentioned, is non-local. But then you find if you look at the commutator, then you find the commutator is 0 for S smaller than the U1 plus U2. So U1 is the Kruskal coordinate for x1, and the U coordinate for x1, and the U2 is the U coordinate for x2. And then become non-zero for S greater than U1 plus U2. And now if you if you translate this operator, so in order to have non-zero commutator with this x2, you have to enter the light cone of x2. Okay, and again, this U1 plus U2 is precisely the law distance. Law distance in taking from this point along the U direction into the light cone of x2. And so this transformation does know this more general causal structure. Okay, not only know the horizon, but actually knows the more general causal structure. And I emphasize the causal structure we see is actually sharp, even though the transformation is non-local. Okay, it's at some sharp value of S, somehow it suddenly become non-zero. Good. And now, so as I mentioned, this transformation is in general non-local, but it turns out that there's one regime. Somehow this transformation become a local transformation. So this is a regime which we take the mass of the particle to be very, the mass of this scalar field to be very large. So this transformation depends on, say, the dimension of the operator, okay? And if we take the dimension of the operator to be very large, by large, we just means parametrically large. Say it's always order 1, independent of n, but parametrically large. And the mass, the dimension of the operator translates into the mass of the scalar field in the park. So if we take these large mass limits, okay, and then we average over the boundary spatial direction, say if we consider the BTZ case, then the boundary spatial direction is a circle, because we are only interested in the physics in the Kruskal plane. So the spatial direction we don't worry about so much. Okay, so if we do that, it turns out that this transformation becomes a local transformation. So take this point, transform to another point in the Kruskal space-time. Again, the Kruskal here is completely emergent. So this transformation is some complicated transformation. Okay, the transformation itself knows nothing about the Kruskal coordinates. So this is some complicated transformation. Then you find you can actually rewrite this the final answer in a very simple form in terms of the Kruskal coordinates. Okay, so the Kruskal coordinate here is completely emergent, and the transformation is like this. So if the initial Kruskal coordinate is given by u0 and v0, don't confuse about this u transformation with u. Here u just means the Kruskal coordinates, and here u means the transformation. They're not the same. So turns out that this the u, the Kruskal view just translate by value s, but the vs transform in this more non-trivial way. Okay. So you can motivate a little bit where this transformation come from. So once you can check is that this transformation actually leaves the boundary. Invariant does not say it takes a point and the boundary still remains in the boundary. Okay, so vs to have this property so that you can do that. Anyway, so if I draw a flow chart, okay, and then the flow chart is like this. If you take initial point, and then as you vary s, and then I will take your point, say go behind the horizon. I can go behind the horizon, and similarly in the left region, and so this is just the s from minus infinity to plus infinity evolution. And so this is the evolution if I do the constant s slice. So if you start the operator start with t equal to 0 slice, and then you look at what is the where does this operator go when you evolve with constant s, okay, and then you find that this initial s initial t equal to 0 Cauchy slice then evolve into those Cauchy slices. Okay, so you cross the horizon extension. And here you can see explicitly near the horizon, near the horizon which v is equal to 0, and then this just become pure a translation in u. Okay.
So in the previous slide, so
sorry?
that I have a question on this this slide. So
okay.
The time, the trajectory and the singularity. So probably not only S0, but there might be some other S.
Right. Yeah, that's a very interesting question. So if you draw this geometrically, and then the trajectory say should end at the singularity. But actually, to see that the singularity, you didn't. Yeah. So you can ask. Yeah, so there's some value of s, okay, this u and v, us and vs will hit the singularity. And then you can ask, geometrically will hit the singularity. And then you can ask the question, does this phi actually become singular at that point? Okay, it turns out this is a rather tricky question, because in this large mass limit, there's some very subtle issues. Say when you go to the singularity, and then when you take the large mass limit, these two limits don't commute. Okay, so in the large mass limit, actually you don't directly see the singularity. Okay. Yeah. So does that answer your question?
Yes. Okay. Thank you.
Good. So now you can also choose some other sub-algebras. So let's choose the sub-algebra to be n, to be all the operators, single trace operator, say at time greater than t equal to 0. Okay, so take the upper half of your boundary space-time. Okay, so this is another sub-algebra which you can show satisfy this half-sided modular inclusion properties. And then again by similar tricks, and then you can argue this is dual to this region. The Bach field, this algebra is due to the algebra of the Bach field in this region, and then you can work out this US explicit. And then that will generate a different flow, okay, different time, a different emergent time. And this time is more like the U translation. a V translation. So near the horizon is like a V translation. Okay, and it's like a V translation. So by choosing different sub-algebras, you can either generate U Kruskal translation, or you can generate something like a V Kruskal translation. And of course, you can also compose them. Okay, you can compose such kind of U-type and V-type flows. And in principle, you can generate any kind of, you can generate, say, infinite time, infinite number of flows. Okay, and including, yeah, just like the Kruskal time flow. And you can also consider, there are also infinite other kind of emergent times. For example, instead of taking, say, n to be all the operator below t equal to 0 slice, you can consider below some slice which actually depend on the spatial direction. Okay, then that will generate some other time which will depend on some other slicing, some other evolution of the block, which will depend on the space, depend on these angular coordinates. Okay, and similarly, you can do the n this way. So this way, you can actually generate an infinite number of times. Okay, so all these times, by definition, they're diffeomorphism invariant because they're intrinsically constructed from the boundary theory. So here we show actually there's an infinite number of this kind of diffeomorphism invariant time actually exists on the gravity side. So this is highly not obvious. Okay, so normally if we talk about the Kruskal time, we say this is just coordinates. Does not have invariant physical meaning corresponding to you fix some gauge, etc. But now we can actually show, actually there's a diffeomorphism invariant way to think about those kind of Kruskal-like time. Again, yeah, again, this is just to summarize the whole story. So if you look at the single slice in the block, and the operator algebra here on this single slice is identified with the boundary theory. So MR tilde is related to MR in the boundary, and ML tilde is related to ML in the boundary. And then the block time evolution is related to the boundary automorphisms. Okay, and if you find some boundary automorphisms with generator who is bounded from below, okay, whose spectrum is bounded from below, and then that gives you a candidate of the block time. And then there's a standard time translation generated by HR minus HL, okay, and then that will generate this kind of time evolution, okay, which never crossed the horizon, and this time translation always exists, okay, regardless of the type of the algebras of ML and MR. So this applies for type 3, 1, type 1 doesn't matter. So this always exists. And also the evolution by HR plus HL, they don't have a sensible argument. But if MR and L are type 3, 1, and then we have this half-sided modular times, which is specific to type 3, 1, and then we can have this kind of flow. Okay, this kind of Kruskal time flow. Okay, and then that can be used to generate the F region and the P region, and also give a sharp signature over the horizon. Again, just to show this picture again, so depend on the type of algebra you have, you either have this picture or you have this kind of disconnected picture. So normally the normal slogan say you have the right and the left are connected because they have a very large entanglement. Okay, so this is the standard ER equal to EPR conjecture. But from this point, from our current point of view, this kind of connectedness we find from this type 3 algebras give you a more refined way, okay, a more precise way to talk about the left and the right. They're really connected. Okay, yeah, ER equal to EPR is more like a conjecture. Say somehow they should be connected, but here we can actually using this emergent type 3-1 properties, we can actually really show they are connected. So any questions on this part?
Well, can I ask you a question?
Yes.
Does this the space the connection of two different space-time and the relation to emergent type 3-1 applies for this eternal black hole only, or any general construction by gluing to space-time?
Yeah, we think so of course we only worked it out for the internal black hole, but I think the concept should be much more general. And for example, you can imagine, consider more general, just some deformation of this internal black hole to make this throat to be much longer, say by sending shock waves, etc. So we believe for that kind of space-time, again, this type 1 3-1 algebra will be able to generate again such a picture. Of course, technically, the story becomes much more complicated. Yeah.
I see. And I have one more question. It's a kind of broader question, but so is this observation from von Neumann algebra has any relation to quantum error correction?
That I'm going to mention later.
Okay.
Yeah, that I'm going to mention later in the last part of my talk. Yeah.
Okay, thanks.
Good.
Can I ask a question?
Okay, sure.
I mean, for instance, I mean, for the eternal traversable wormhole, which has a left-right two-sided structure. There, for instance, I mean, we can try to do the similar construction.
Yeah.
And then certainly there, we don't have a horizon structure at all. Causality, bulk causality will be there, I expect. But
sorry, I'm not sure I completely understand you. So you say you want to consider
eternal traversable wormhole geometry.
Yeah, you want to couple the left hand, the CFTL and the CFTR by some.
That's right. From the beginning.
Yes. By some double trace operator. Then you can do the similar construction. Then the algebraic structure changes a little bit. So there you still have a horizon, but then there's an opening in the middle, say of this Kruskal diagram, that you can actually go now from the left to the right. Okay. Indeed, the algebraic structure will change in that story. It's a very interesting example to understand more precisely. Yeah.
Okay.
Yeah. Good. Other questions? Okay. Yeah. Then let me just go to the third, the last part of my talk. So this part will be in the paper, which to appear soon. So let me just again mention something I discussed in the first lecture. So when we do the holographic duality at the Najian, say we have some boundaries, semi-classical boundary states. So I defined what we mean by these semi-classical states, which have a well-defined Najian limits, and then should be dual to some geometry, and then the GNS Hilbert space around these states, then it's identified with the Fock space around the geometry, and then the operator algebra should also be identified. So let me now denote the operator algebra on the left-hand side to be M psi, and then the operator algebra for this Fock space to be M tilde psi. So this is the Bach operator algebra on the full Hilbert space here, and this is an algebra on this field. Just denote this algebra, and then we have this equality. Okay. And so also that both of them, and on the left-hand side is generated by generalized free fields, and the right-hand side is generated by free fields. Okay. And the generalized free field are the representations of single trace operators, say in this Hilbert space, and then the free fields on the right-hand side are the perturbations of the Bach elementary fields. Then of course they act on this Fock space. Okay. So here is the general picture of the duality in the large n limits. Okay. So now let's consider a causally complete Bach space-time region B. Okay, just imagine you have some space-time, some Bach geometry, and now let's consider some causally complete region B, that's the space-time. So yeah, as I mentioned, the Bach theory essentially, when you take the perturbative expansion in G Newton, you essentially just get a quantum field in the curved space-time. And then the Bach field operator algebra in which I call y tilde B in B should be type 3-1. So this just from the then of course this tilde YB is a sub algebra of the full operator algebra acting on of your Fock space. Okay, of Fock space. And now from the identification of this Fock space from this M psi tilde, okay, so we have this M psi tilde is the operator on the Fock space. It's identified with operator algebra on the GNS Hilbert space. Then that means there must be an emergent type 3-1 sub-algebra of this M psi Y, and this Y is equal to a Y tilde B. Okay, so there must be a counterpart of it because this two is identified. And if you have a sub-algebra here corresponding to region B, then there must be a sub-algebra here. Okay. So that tells you for any causally complete the Bach space-time region, there must be an emergent type 3-1 sub-algebra in your boundary theory. Okay, which is identified with the algebra in that region. So this is essentially established just from the duality. Okay. But now, conversely, we like to conjecture that if you given any type 3-1 sub-algebra Y of your full operator algebra, there exists some Bach region B that the operator algebra in that B region B is equal to this Y. Okay, so this this converse direction is a conjecture. Okay, at the moment it's a conjecture. We don't have a precise proof of it. Okay. And then we can generalize the story we have for the black hole case to this story. Okay, just to give you a general picture, and then to see how the geometric properties, say, of this region B can arise from this kind of identifications. Okay, so if imagine you have some kind of causally complete region in the Bach, which is this region B, and then the internal time of B then can be just described by the modular flow, say, of Y, of this emergent type 3-1 algebra in the boundary corresponding to B. And then the global time which flows, which take, yeah, if you can have time which flow within the B, you can also have time which take you outside the B. Okay, so this kind of global time, again, this time is not unique. You can have infinite number of them. This kind of time flow take you outside B, then this is described by the half-sided modular flow. Okay, so this is the analog of the Kruskal time for the black hole case. Okay, for the right region of the black hole case. And then the light cone boundary of this B and the corresponding causal structure then should appear as non-analytic behavior under this half-sided modular flow. Okay, when you act this half-sided modular translation, okay, on your operator inside the B, and then that can take you outside the B. And when you take outside B, then again, when you cross the boundary, there will be non-analytic behavior. Okay, so so this is just the generalization of the picture we obtained from the black hole. So so essentially, this tells you that essentially all these geometric properties associated with some local Bach region, we should be able to obtain from properties of this type 3-1 algebra. Again, yeah, again, this is the slogan I mentioned at the beginning, that the type 3-1 modular algebra is one-to-one correspondence with some Bach space-time region, and then identified with Bach algebra and the properties of this type 3-1 algebra related to the geometric notions, etc. And then the slogan we want to give is that the box spacetime is because if you know all the locals region, the union of all this local space-time region in the box, of course, is the full box space-time. Okay, and so you can say that the box space-time is a geometrization, say, of just emergent type 3-1 algebras. Alternatively, we can say the box locality, okay, because we can really probe the local regions in the box, arbitrary local regions in the box. So you can say the box locality is actually a geometrization of emergent this type 3-1 algebra of the boundary. So let me just show you some examples of this kind of correspondence. So one example we already discussed before is that if you take the boundary theory, take this, take the algebra of the t smaller than 0, say in the sum of your double states, and then we already argued that this should be dual. Yeah, I just mentioned this without we show this explicitly in the paper, and then this can be shown to be identified with the algebra of operators in this Entanglement region in the black hole geometry. Okay, yeah. So conversely, the operator algebra in this region of Entanglement is dual to this type 3-1 algebra in this region. And yeah, so this kind of region is called the time band, okay, because this is not just the standard causal dimension. So it's a boundary theory, this is a time band. So we can consider also other kind of time bands, for example, in the vacuum. So let's consider safety 2, say, just for simplicity, let's consider 2-dimensional safety in the vacuum. And so suppose this direction is x, this direction is t. So let's again consider time bands between t1 and t2. And with the width of the time band to be smaller than pi r. So r is the radius, ADS radius. So if you consider the algebra in this region, okay, then we can show this is actually this operator algebra in this region is a dual to the Bach algebra in the shaded region. Okay, so the Bach dual here, because we can see the CFT in the vacuum. So the Bach geometry is just a cylinder which has suppressed the circular direction, so the x direction, the circular direction, and so it's just a cylinder, and then yeah. So you should imagine you should rotate the whole picture by 2 pi, okay, and then yeah. So this the operator algebra in this time band then is dual to this spherical window region. Okay, because you're supposed to rotate it by 2 pi. Okay. So from the top, so if you view it from the top, so on the single slice, on the single time slice, and then yeah, so this is the boundary, and this is the boundary, and the shaded region is the region of the operator algebra, which is dual. It's the Bach region, which is dual to the operator algebra in this boundary. Good. And interestingly, if you consider this time band for CFT2 in the vacuum, if you consider this time band to be large enough, say greater than pi r, so greater than pi r, and then you find actually the operator algebra here is dual to the full Bach operator algebra. Okay, you just dual to the full Bach operator algebra. Okay, so so this actually can be understood by the fact that in the vacuum, the operator spectrum is actually quantized. Yeah, the spectrum for Bach field is actually quantized, and so yeah, I can actually show this explicitly. Good. So we can also consider.
Excuse me.
Yeah.
What was R?
Sorry.
What was R?
Oh, R is the radius. It's the ADS radius.
ADS radius.
Yeah.
Also, even in this boundary perspective, the ADS radius is needed.
Yeah. Yeah. Here we just consider the standard.
Yeah.
Yeah,
For
yeah. Here we
example,
just consider the standard story that the bark is the ADS on the cylinder. It's a global ADS on the cylinder with radius r, and then the boundary would be, say, a CFT on the boundary of that cylinder. Okay. Yeah, the boundary is a cylinder, and the bark is a solid cylinder. The boundary is a cylinder with a radius of 2 pi r. Yeah, with radius r. Yeah.
okay.
Yeah, yeah. The r is just the radius of the boundary CFT. So you can also, yeah, as the sub cases is the previous sub-region duality. Okay, so previous sub-region duality, they become a subcase, the subcase, and then can now be formulated actually without referring to entropy. So let's consider, say, the boundary CFT in the vacuum, again in the vacuum state, and some region R. Okay, and then we can so at the finite end, the full operate algebra in R is type 3-1. Okay, this is just because the CFT is a quantum field theory, but this type 3-1 algebra is irrelevant in the large n limit. It's because, as we mentioned, when you take large n limits, many operators in your original operator algebra, they actually disappear. Okay, and so this is no longer makes sense. Yeah, so this algebra no longer makes sense in the large n limit. So this is just irrelevant. So in the large n limit, we now need to consider the sub-algebras of the single trace operator algebra associated with this region. Okay, or its causal complements. And now, yeah, I will not go into details here. And then there can be multiple choice of them, okay, of the algebras, single trace algebras associated with this R, depending on how you take them. And so we conjecture them to be type 3-1. In the case of Windler, you can show this explicitly, but for the general regions, this is a conjecture. And then these sub-algebras then can be identified with Bark operator algebra, say in the entanglement wedge or in the causal wedge, etc. And so the largest one then can be used to define the entanglement wedge in the Bark. Okay, so essentially define the entanglement wedge to be the region in the Bark whose operator algebra is equivalent to this operator algebra, or say the largest operator algebra associated with this region. And so recall, normally the entanglement wedge is defined as a causal completion of this region between the RT surface and the some boundary region R. So again, this is the one single slice of the ADS, and the boundary is a circle. And then suppose you consider some region R, and this ER would be the entanglement wedge on this slice, okay, on this time slice. And this is the RT surface, and then the entanglement wedge is the causal completion of this region. Okay, and so the standard subregion duality says that the subregion duality says that the physics of region R should be equivalent to the physics in this region, in the causal completion of ER, and which is defined whose boundary is given by the RT surface. So here, by identifying the algebra between the boundary and the Bark, we provide an independent definition of the RT surface without using the entropy. So here, the RT surface is just the boundary of the region whose algebra is identified with this boundary algebra. So I emphasize that the boundary entanglement emergent algebra actually knows the full causal completion of the entanglement wedge. Okay, just not only on the single spatial slice, but actually the full causal completion. So these claims can be proven or verified in the simple cases. Okay, so for example, in the half space for general boundary CFT in the vacuum. So this is more like a Windler story. And then you can show, and then this is dual to ADS Windler region, and then you can show this explicitly. And also by conformal transformation, in the vacuum, you can just apply this also to the spherical region for boundary CFT. Okay, because they this half space, this Rindler and this spherical region, they're just related by a conformal transformation. So in these cases, the causal and the entanglement wedges agree. Okay, so these are the very simple cases. So here are some examples which we have worked out explicitly. So suppose you consider the Poincare patch, and you consider the half space. Okay, just the half the boundary region given by the half space. And again, this is just one single slice in the block. So this is the radial z direction of the Poincare coordinates, and this is the boundary spatial direction, which I suppressed at the time. So, and then you can show that the block region whose orbit algebra is equivalent to the boundary algebra in this half space is precisely this shaded region. Okay, and this is also exactly given by, just trivially given by the RT surface. And so for this example, this provides the derivation, say, of the RT surface. And similarly, if you consider a segment, okay, and then you find that the Bach region, again, this is just on the single time slice, and the Bach region whose orbit algebra is equivalent to the boundary algebra in the R region is the field within this half circle. Then of course this is just the standard RT surface for the for segment in the CFT2. Okay, so these are all in the CFT2. So slightly more non-trivial example is the case you consider two half space. Okay, so the R consisted as two disjointed half space. Okay, so this going to infinity in that direction, and this going to infinity in that direction, and then separated by some segments. Okay, so the R region now become two segments, and both are half space. Okay. So in this case, then you find the region which is equivalent to the boundary algebra is given by this region, this shaded region. Okay, and this is precisely the entanglement wedge you would find from the RT surface. Okay, again, this provides a derivation of the RT surface for this case. And this is a non-trivial example because in this case, the causal wedge is different from the entanglement wedge. So the causal wedge just corresponding to, you just do the separate wedge, do the separate equivalence for these two segments. Okay, because each one is a half space, and you just add these two together. That's the causal wedge. So this is a non-trivial example, which this algebraic equivalence actually lost the entanglement, the difference between the entanglement wedge and the causal wedge. Okay. And here, even though I'm drawing the full, only a single time slice, and actually the full the causal completion actually can be shown explicitly following the equivalence of the algebra. Okay, yeah. So here I'm drawing using the Poincare picture by a conformal transformation. You can map it to the global ADS. So the boundary of the Poincare picture, say for CFT2, is just a single line, and then of course this is mapped to the boundary of global ADS with 1 point removed. Okay, with 1 point removed. And then this two half space separated by some segments, and in the Poincare case, then corresponding to this cylinder, which you have this two region, and then separated by this point which is removed on the circle. And then again here the causal wedge is given by this, and the entanglement wedge is given by this. And so this is a non-trivial example which the entanglement wedge is greater than the causal wedge. So here let me just quickly mention. So compare with the previous formulation of sub-region duality, the new formulation actually has a number of conceptual advantages. First, the sub-region duality previously was never precisely defined. So most of the time, people just vaguely say the physics in this boundary subregion is equivalent to the physics in this Bach subregion, but it's never specified precisely what physics they're talking about. And the one precise formulation was using this quantum error correction by Dong, Harlow, and Wall. But there, they have you to use the finite dimensional Hilbert space. They have to assume that the Hilbert space is factorized between different regions, etc. But then that actually does not apply to realistic ADS-CFT examples, because as we emphasize, the Hilbert space can actually not be factorized. But the factorization of Hilbert space play a crucial role in their construction. And second, actually, even in the previous story, there's a tension. Yeah, I would say the tension, there's some kind of funny thing regarding the definition of the RT surface. So we define the RT surface by saying this is give the entanglement entropy of the boundary series. But strictly speaking, the entanglement of entropy of the boundary series is just not defined. Because if you strictly work with a continuum limit of the boundary series, the entropy is not defined, the entropy is infinite. So it's not a properly defined quantity. You have to introduce some regularization, etc. But on the other hand, the RT surface, the minimal surface, is a precisely defined quantity which you can define precisely on the gravity side without using any regularization. Okay, in the G-Newton goes to zero limit. So somehow you are using something which is not precisely exist, strictly speaking, does not exist, somehow to define something which is actually precise, can be precisely defined. So there's something funny here. But it is algebraic definition, and then give you resolves that kind of tension. Okay, all quantities can be precisely defined, and so you don't have to rely on this entropy. And then finally, this JLMS equivalence proposed by JML equivalence between the Bach and the boundary relative entropy and the equivalence of boundary and the Bach modular flow. So that follows immediately from here. So once we identify the Bach algebra with the boundary algebra, then just automatically that their relative entropy must agree and that their modular flow must be the same. Okay, so this just follows trivially from here. But in this original Jeffrey, Snookowitz, Marcina, and the Sue story, to using the entanglement entropy, RT formula, etc., they have to, argue in somewhat indirect way. So here it just follows immediately.
Excuse me. Excuse me. As for the point 3, I think they decompose the boundary modular Hamiltonian into the area operator, which is the center, and the rest of the modular Hamiltonian. But in your formulation, is it possible to define area operator?
No. So that's precisely the advantage here. So in their story, they have to do that decomposition, and that area operator then does not play any role because compute with everything, and then does not play any role. So in essence, they were identifying the modular operator on the Bach part, and with the mod. So here we just have two algebras. They're equivalent, and you just identify the modular flow, and they're just automatic. You don't have to do this decomposition, etc. You don't have to do this argument. They have to make some indirect arguments.
I see. Thank you.
Okay, so I'm running already over time. So I have one final small thing to say about this emergent quantum error correction properties, and So yeah, maybe you can tell me what I should do.
You can spend time, no problem. So you can
Okay,
go ahead.
okay. Yeah, then maybe I will just quickly tell you this story because yeah, this story is very simple and I can just do it in a few minutes. So when you have this sub-region duality, say if you imagine you have some operators in this region B, and then that can be, suppose this B is in the intersection of the entanglement wedge for A and A prime. Okay, so suppose this is the region of A prime, and then this gamma A is the RT surface, and then this defines this entanglement wedge for A, and similarly you have A prime, and if you have some B, which is in the intersection of these two regions, okay, and then this B can be described both in terms of algebra of A and also the algebra of A prime. Okay, so this kind of sub-region duality that implies that the Bach description is actually highly redundant. Okay, in principle, you can find an infinite number. Okay, as far as B is lies within their intersection, you can find an infinite number of the boundary region, which B can all be reconstructed. Okay, and so here I emphasize one story. It's that in order for this story to be non-trivial, so the B should lie within the region. Yeah, so here the non-trivial aspect is the following, okay? So you have this region A, and then you have this entanglement wedge for A, and then you have this entanglement wedge for A prime. And then there's an intersection between the entanglement wedge of A and A prime, which is this region. But you can also, in the boundary, you also have the intersection of A intersection with A prime. Okay, and the intersection of A and A prime in the boundary it also have its own entanglement wedge, which is this blue shaded region. So the non-trivial thing is that the intersection of EA and EA prime is actually greater than the entanglement wedge of their boundary intersection. Okay, so only for B in this region is the story non-trivial, because if B is in this blue region, then this is just the trivial story because it's already because you are already in the intersection between between these two regions, and it's in so here this arrow correcting story which is non-trivial is that the highly non-trivial story is that the entanglement wedge for the A intersection with A prime is a subset of their individual intersection of their individual entanglement wedge. Okay. So this has been given, say, this beautiful interpretation in terms of quantum error corrections. Okay, and because now you can eliminate, say, part of your boundary, you can still recover the algebra. Okay, and this quantum error correction story provides the guiding principle for building many toy models of holography using finite dimensional Hilbert spaces or type 1 algebras. So in some cases, you can also do infinite dimensional Hilbert space, but it's always a type 1 algebras. Okay, so that's why I call them toy models. But this error correction story never explains the physical origin of the quantum error correction properties. Okay, just say, oh, this Bach property reflects that somehow whatever states describe the geometry must be a quantum error correction code. Okay, and then they prove some equivalence statements. Okay, so but the physical origin of the quantum error correction is never clear. And also in real holographic systems, say for example for super Yang-Mills theory, there's really no choice for quantum error correcting codes. Okay, it should be just intrinsic property of the large element. So just take the vacuum of the A=4 super Yang-Mills theory, then you must have this kind of property. Okay, take the sum field double of the A=4 Yang-Mills theory, you must have this kind of property. And so this must be some kind of intrinsic property of any semi-classical states. okay, of your boundary theory. Okay, you don't really have to do anything, say, to construct the code. So indeed, you can show that indeed this is an intrinsic property with this recognition of this type 3-1 algebra. Let me just tell you very quickly this aspect of the story. So now let's just imagine we have a boundary theory again. Just consider one dimension, one spatial dimension, and the time, the horizontal axis is spatial direction, and the vertical time. So let's consider just some region, a causal diamond R1. Okay, and so this defines some algebra in this causal diamond. And now let's consider some causal diamond R2, which they can intersect with R1, and then this is the intersection region. So if you consider ordinary quantum field theory, including n equal to super Yang-Mills at the finite n, and then what you have is just say this boundary, you can deduce this just from the boundary geometry. Say if you have operator algebra in R1 and operator algebra in R2, then the intersection of R1 and R2, okay, is just this diamond region, okay, diamond region, and that is the same as operator algebra of R1 intersection with R2. Okay, this just follows from the you can choose from the Cauchy slides, yeah, just from trivially from the standard statement. But if you have infinite n, then we have something different. And now we need to consider the single trace operator algebras. So as I emphasized before, single trace operator algebra is very different from the standard operator algebra for standard quantum field theory. Because at a different time, the single trace operator algebra are inequivalent from each other. So for example, this BR1 for the standard quantum field theory or for the angle to super Yang-Mills at finite n, it can be determined by the operator algebra just on this single Cauchy slice, okay, just on t equal to 0 slice. But this is not the case for for this single trace operator algebras. Okay, so that means they have some new features. So the new features here, which is unintuitive, is that it turns out if you look at the intersection of the single trace operator algebra associated with the intersection of R1 and R2, okay, in this shaded region. Now it's actually a subset of the algebra of R1 and it's intersect with the algebra of R2. Okay, so for standard quantum field theory, this equivalence just follow from this this geometric argument on the boundary. But somehow, when you look at single trace operator algebra, and this geometric property breaks down. Okay, and the breakdown of this geometric quantity precisely is reflected in the bulk through that. Now each of them is just identified with the entanglement wedge of each region. And the fact this is a subset of that, it just tells you that there's this actual red region. So we see this quantum error correcting property of the bulk is just precisely a geometrization of these unintuitive properties of the single trace operator algebra. Okay. Essentially, just now when you translate this story into the bulk, and now this relation becomes geometric relation. Okay, but in the boundary, this is a highly non-trivial relation. You have to work very carefully. Okay. Good. So let's conclude my discussion. So yeah, since it's running late, let me just show my final slides. Some future perspectives. Okay, let me just stop here.
Thank you very much for a great talk. Yeah, please ask question. Let me ask one question in here in the future perspective. So this island story is very interesting. So there you also consider some ADS coupled to some best CFT there or so?
Yeah, that's right. That's right.
I see.
So yeah, so here, yeah, of course, I'm just listing here as future directions.
Yeah.
Here, I just want to convey the sense that the potentially the derivation of the island can be much more natural in this story.
Yeah.
It's because the say now imagine you just couple your CFT to a bus, and then again the bus have operator algebra, and now you can just ask which part of the box space-time somehow captures somehow it's become equivalent to this operator algebras, say on the boundary and the box, etc. And then from there, just like we derived the RT surface and this entanglement wedge for those simple shapes, and in principle, you can also be able to derive the islands. Yeah, because the island is also just some more general entanglement wedge.
Then let me ask the next question or related to that. Probably someone asked in the previously, but here you talk about the eternal black hole and this kind of the emergent time. For the evaporating black hole, like a one-sided, here you also mentioned a single-sided. There you also have some similar, like some in the past. I remember some people like talk about the mimic the Sommerfeld double to construct the evaporating black hole, probably Yandebo or their collaborator. So do you have also have in mind that kind of picture or something else?
Right. Yeah. Yeah. I think the previous people have written a lot about this single-sided black hole story. Say most particularly this Papadodimos and Raju, which they try to construct this mirror operator, and then make that story then become similar to Sommerfeld double story. So I think that their general picture, the general idea is correct, and just in terms of in terms of this more precise language, so yeah, just everything can be understood more precisely. Yeah.
Okay. Can I ask you a question?
Yeah.
So previously you defined how to characterize the horizon in terms of operator. Now, is there any notion of the general gluing of the space-time in terms of the operator algebra?
Sorry, by gluing of the space-time, you mean?
For example, the people talked about the gluing space-time in terms of entanglement.
Oh, right. Yeah.
So
right.
Is there any similar notion here?
Yeah. I think this actually provides a more precise way to talk about the gluing the space-time than the previous story. Previous discussion is always heuristic. And here you actually have a precise language to talk about that.
So can you remind me what was that?
You mean the previous story or the current story?
No, the current story.
Yeah, the current story is just now. You can just if the for example in this black hole case, in this internal black hole case, if the left and the right are connected.
Yeah, but if not the I guess the black hole. I mean the if general, I mean the space-time gluing is similar.
Yeah.
I see.
Yeah. Just say, if you can start with operating the right region, you evolve it by some operator, by some evolution operator, and then it can now have non-trivial computation relation with the left CFT, and then these two CFT, of course, must be connected. So this is the precise notion to say the two are connected.
I mean that's the confusion. I mean if horizon and the non-horizon is similarly characterized, what is the particularity of the horizon? what happens more at the if the surface, the gluing surface is the horizon?
Oh, you're asking what happens if the gluing surface is not horizon?
No, if it is the horizon compared with the non-horizon.
Oh, yeah. So here for the internal black hole, the gluing surface is the horizon.
Yes.
And in the case of the which is the non-horizon, and then the normally corresponding to some kind of entanglement extremal surface corresponding to the entanglement wedge. So here, of course, we don't have that requires very detailed discussion, etc., to really prove the statement. So here, say, argued in principle, this algebraic approach can fully recover the entanglement wedge. So if you can recover entanglement wedge, then you can see again to see the connection.
Thank you for the answer.
Yeah.
Any other question?
So I have a question about the type 2 algebra in your final slide. So in your talk, you explained that at finite n, bounded operator algebra is type 1, but full operator algebra is type 3, 1. Right? So then my question is this type 2 algebra is for bounded operator algebra or full operator algebra?
Yeah, it's everything here is bounded. Yeah, you consider some bounded version of the
okay. Then if we consider full operator algebra, so what is the type of algebra? Type 3 1?
Sorry?
So if we consider full operator algebra at finite n or large n, so
I'm sorry. Maybe.
So what is the type of polynomial algebra for full operator algebra?
Sorry, I didn't hear the first part of the sentence very clearly. Can you say it again?
So if we consider full operator algebra, not a bounded operator algebra, so what is the type of polynomial algebra?
No, we cannot talk about that. Because once you talk about unbounded operators, we don't know really how to classify them. So all these classifications, they're about the bounded operators.
Okay.
Yeah. So I think all this discussion here is based on the belief. Yeah, of course, I don't have a proof. It's based on the belief that just by restricting the bounded operators, it's enough to capture the already the key physics.
Okay, thank you.
Yeah.
I have a question. If you consider traversable wormhole, then a bulk operator in some region can be expressed in terms of CFTL and CFTR. But in that case, actually, we need not have S0 like the horizon. So in that case, does that case support? Can that case be supported from type 3-1 Von-Neumann algebra, or do we need different type of algebra?
I think the type 3-1 should be, say if we consider leading order in the large n, or particularly in 1 over n, and so still you will just get type 3-1, and you just say the nature of the type, it just the content of the type 3-1 algebra will become different. Yeah, now they will be dual to different space-time regions rather than
Okay, thank you.
Is there any other question? If not, let's speaker again.